Welcome, gentle soul, however you've arrived here tonight, whether winding down from a long day, settling into a quiet room, or simply searching for a calm voice to keep you company in the dark, you're welcome. There's no rush in this place, no deadlines, no tasks left undone that cannot wait until morning. For now, you are exactly where you need to be. Let your shoulders soften. Let the weight of the day begin to dissolve. And if sleep finds you before we reach the end of this journey, that is perfectly fine. The wonders we explore tonight will be here whenever you return. Tonight, we are going to ask one of the simplest and most profound questions in all of science. It is a question that a child might ask while lying on their back in a garden, staring upward. It is a question that has haunted some of the greatest minds in the history of physics. And it is a question that even now, after centuries of discovery and decades of space telescopes and satellites, has not been fully answered. The question is this: why is the universe dark? It sounds almost too simple. You look up at the night sky and it is black, dotted with points of light. Of course it is dark. But the deeper you look into that darkness, the stranger it becomes. There are hundreds of billions of galaxies out there, each containing hundreds of billions of stars. If you could see far enough in every direction, every single line of sight should eventually hit a star. The sky should be blazing with light. It should be white hot in every direction, and yet it is not. The sky is dark, and in that darkness lies one of the deepest mysteries the universe has ever offered. We will explore that mystery tonight, gently, slowly, one quiet wonder at a time. Some of these discoveries will be about light, some about shadow, some about the strange and invisible substances that make up most of reality but have never been seen. And some will be about the nature of darkness itself, what it is, what it hides, and what it might be trying to tell us. If these calm explorations help you unwind, a gentle tap on the like button or a quiet subscribe would mean more than you know. It helps other restless minds find their way to this place. And that is how we grow this little corner of peace, one sleepy soul at a time. Now, let us begin. There is an old paradox in astronomy, first described in its modern form by a German physician and astronomer named Heinrich Wilhelm Olbers in the year 1823. The paradox goes like this: if the universe is infinite and filled with an infinite number of stars, then no matter which direction you look, your line of sight should eventually land on the surface of a star. Every point in the sky should be as bright as the surface of a star. The entire night sky should glow with a uniform, blinding radiance, as bright as the sun in every direction. And yet it does not. The night sky is dark. Olbers wanted to know why. The paradox is named after him, but Olbers was not the first to notice the problem. As early as 1576, the English astronomer Thomas Digges considered the question when he proposed that the stars extended infinitely outward in every direction. If that were true, he realized, the sky should never be fully dark. The darkness of night was, in his framework, a contradiction. Johannes Kepler also wrestled with this problem in the early 1600s. For Kepler, the darkness of the night sky was evidence that the universe could not be infinite. If it were, he argued, the heavens would be ablaze. The fact that they were not meant that somewhere, in some direction, the stars must come to an end. Darkness, for Kepler, was the edge of creation made visible. Even the poet and writer Edgar Allan Poe considered the paradox. In his 1848 prose poem Eureka, Poe suggested that the reason the sky is dark is that the universe is not old enough for light from the most distant stars to have reached us. It was a remarkably prescient thought for a writer known more for ravens and dark cellars than for cosmology. And as it turns out, Poe was closer to the truth than many of the scientists who came before him. The simplest resolution to Olbers's paradox is not that the universe is small. It is not that there are too few stars. It is that the universe has a finite age. Light travels at a fixed speed, roughly 186,000 miles per second, and the universe is approximately 13.8 billion years old. That means there is a limit to how far light can have traveled since the beginning of time. We cannot see stars beyond a certain distance, not because they do not exist, but because their light has not had time to reach us. The darkness of the night sky is not an absence, it is a horizon, a boundary drawn not by space, but by time. But that is only the beginning of the answer, because the universe is not just old, it is expanding, and that expansion changes everything about how light travels through space. In the year 1929, an American astronomer named Edwin Hubble made one of the most important discoveries in the history of science. By studying the light from distant galaxies, Hubble noticed something remarkable. Nearly every galaxy he observed was moving away from us, and the farther away a galaxy was, the faster it was receding. This was not because Earth occupied some special or central position in the cosmos. It was because space itself was stretching. Every point in the universe was moving away from every other point, like dots painted on the surface of a balloon as it inflates. The galaxies were not flying apart through space. Space itself was growing, carrying the galaxies with it. This discovery had a profound implication for the darkness of the sky. As space expands, the light traveling through it gets stretched along with it. A wave of light emitted as visible blue might arrive after billions of years of travel through expanding space as invisible infrared or even microwave radiation. The light is still there, but it has been stretched beyond the range of human vision. The universe is not dark because it lacks light. It is dark because much of its light has been shifted into wavelengths our eyes were never built to see. This stretching of light is called cosmological redshift, and it is happening to the light from every distant object in the universe. The farther away something is, the more its light has been stretched, and the more invisible it becomes to human eyes. A galaxy 10 billion light-years away is not merely faint. Its light has been redshifted so dramatically that it has left the visible spectrum entirely. It is glowing, but glowing in a language our eyes cannot read. If you had eyes that could see in the microwave part of the electromagnetic spectrum, the sky would not look dark at all. It would glow faintly in every direction, a soft and nearly uniform warmth filling the entire sky. That glow is real. It has been detected, measured, and mapped in exquisite detail. It is called the cosmic microwave background, and it is one of the most important discoveries in the history of cosmology. We will return to it later in our journey. For now, simply know that the darkness you see when you look up is not complete. It is filtered. The universe is full of light you cannot see. There is a measurement in astronomy called the extragalactic background light. It is the total amount of light produced by every star and every galaxy that has ever existed throughout the entire history of the universe. Scientists have attempted to measure this cumulative glow using space telescopes that can detect light across a wide range of wavelengths. The result is staggering. The total amount of starlight ever produced is estimated at around 4 times 10 to the power of 84 photons. That is a 4 followed by 84 zeros. An almost incomprehensible flood of light has been poured into the cosmos over the past 13 billion years. And yet, when you measure the brightness of the night sky between the stars, it is breathtakingly faint. Most of that ancient starlight has been redshifted, scattered, or absorbed. The photons are still out there, traveling through the void, but they are spread so thin across the expanding universe that the sky remains, to human eyes, dark. The darkness is not emptiness, it is dilution. A vast ocean of ancient light stretched too thin to see. Light does not last forever in the same form. A photon emitted from a star may travel for billions of years without striking anything, crossing voids so vast that no atom interrupts its path. But even in that emptiness, the photon is changing. As the universe expands, the space through which the photon travels is stretching, and the photon stretches with it. Its wavelength grows longer. Its energy decreases. A photon that began as ultraviolet light might, after billions of years of cosmic expansion, arrive as a gentle pulse of infrared. It has not been destroyed. It has been transformed, cooled, softened. The universe does not erase its light. It simply whispers it quieter and quieter, until only the most sensitive instruments can hear. There is a region of the electromagnetic spectrum called the cosmic infrared background. It is a faint glow that permeates the entire sky, detectable only with space-based telescopes that have been cooled to near absolute zero to prevent their own heat from drowning out the signal. This glow is the accumulated infrared light from every galaxy that has ever formed and every star that has ever burned. Some of it redshifted from visible wavelengths, some of it emitted as infrared from dust-shrouded galaxies in the early universe. NASA's Spitzer Space Telescope and later the James Webb Space Telescope have both contributed to mapping this faint cosmic warmth. It is everywhere. It fills the sky in every direction, and it is completely invisible to the naked eye. The night sky is dark only in the narrow band of light that human evolution has equipped us to perceive. There is something called the zone of avoidance. It is a region of the sky where our view of the distant universe is blocked not by cosmic darkness, but by our own galaxy. The Milky Way is a flat disk of stars, gas, and dust, and when we look toward the plane of our galaxy, the dense clouds of interstellar dust absorb and scatter the light from everything beyond. Roughly 20% of the sky is obscured by this band of galactic material. Behind it, hidden galaxies and galaxy clusters exist that we have only been able to detect using infrared and radio telescopes, which can peer through the dust that visible light cannot penetrate. The darkness in the plane of the Milky Way is not cosmic emptiness. It is a curtain. And behind the curtain, the universe continues. When astronomers point their telescopes at the darkest, most empty-looking patches of the night sky, they do not find nothing. In 1995, the Hubble Space Telescope was aimed at a tiny patch of sky in the constellation Ursa Major, a region so small it could be covered by a grain of sand held at arm's length. The patch appeared completely black to ground-based telescopes. There was nothing there. But Hubble stared at that blank spot for 10 consecutive days, collecting every faint photon that arrived. When the image was assembled, it contained over 3,000 galaxies. Not stars, galaxies. Each one containing billions of stars, all hiding in a speck of sky that appeared to the naked eye to be pure darkness. That image became known as the Hubble Deep Field, and it changed the way scientists understood the universe. If a random, empty-looking pinprick of sky contained thousands of galaxies, then the entire sky must contain hundreds of billions of them. Later observations, including the Hubble Ultra Deep Field in 2004 and the Hubble Extreme Deep Field in 2012, pushed even further, revealing galaxies so distant that their light had been traveling for over 13 billion years. These were galaxies that formed when the universe was only a few hundred million years old, infant structures glowing faintly in the ancient dark. The James Webb Space Telescope, launched in December 2021, has since pushed this boundary even further. Its infrared instruments can detect light that has been redshifted far beyond what Hubble could see. In its first deep field image, released in July 2022, Webb revealed galaxies that appeared as faint red smudges, their light stretched by the expansion of the universe into wavelengths that only an infrared telescope could capture. Some of these galaxies may have formed within the first few 100 million years after the Big Bang. They are among the oldest structures ever observed, and they were hiding in what appeared to be empty, dark sky. There is a number that astronomers use to describe how many galaxies exist in the observable universe. For years, the estimate was around 200 billion. But in 2016, a team led by Christopher Consolis at the University of Nottingham published a study suggesting the number might be closer to 2 trillion. 2,000 billion galaxies, most of them too faint, too distant, and too red-shifted to be seen even by our most powerful telescopes. The observable universe is not mostly stars and light. It is mostly the spaces between them. And those spaces, dark as they appear, are filled with light that has been stretched into silence. If you could somehow freeze the expansion of the universe and let all the light from every star in every galaxy travel freely until it filled all of space, the night sky would not be dark. It would glow. Not with blinding intensity, but with a soft, warm luminance in every direction. The darkness we see is a consequence of motion, of expansion, of time. It is the universe outrunning its own light. There is a concept in cosmology called the particle horizon. It represents the maximum distance from which light could have reached us since the beginning of the universe. Because the universe is 13.8 billion years old, you might expect this distance to be 13.8 billion light years. But because space has been expanding during all that time, the actual distance to the particle horizon is much greater, approximately 46.1 billion light years in every direction. This means the observable universe has a diameter of roughly 93 billion light years. Everything beyond that sphere is invisible to us, not because it does not exist, but because its light has not yet had time, even traveling at the ultimate speed limit, to cross the expanding gulf between us. What lies beyond the particle horizon is one of the great unknowns. The universe almost certainly continues beyond the edge of what we can see. There may be galaxies, stars, and structures stretching far beyond our observable sphere, perhaps infinitely far. But we will never see them. Their light will never reach us. The expansion of space carries them away faster than their photons can close the distance. The darkness at the edge of our vision is not a wall. It is a receding horizon, moving further away with every passing moment. Every second, the observable universe grows slightly larger as ancient photons, having traveled since nearly the beginning of time, finally arrive at the edge of our detection. But at the same time, the most distant galaxies we can currently see are being carried beyond our reach by the accelerating expansion. There is a boundary called the cosmic event horizon, beyond which no signal, no matter how long we wait, will ever reach us. Galaxies that are currently visible will eventually cross this threshold and fade from view. The observable universe is not fixed. It is slowly being emptied, and the sky, already dark, will grow darker still over the eons to come. Light from the most distant known galaxies has been traveling for over 13 billion years. When that light began its journey, the universe was a fraction of its current size. The galaxies that emitted that light were much closer to us then, perhaps only a few billion light years away. But during the billions of years it took for their light to cross the void, the universe expanded enormously. By the time the light arrives, the galaxy that emitted it has been carried to a distance of more than 30 billion light years. We see it as it was, not as it is, and where it is now we may never know. There is something poetic about the fact that every deep image of the universe is also a time machine. Light travels at a finite speed, so looking deeper into space is identical to looking further back in time. The Hubble Deep Field does not show us the distant universe as it is today. It shows us the distant universe as it was billions of years ago. The galaxies in that image may no longer exist in the forms we see them. They may have merged, evolved, or been consumed by larger structures. We are looking at ghosts, bright memories of objects that have long since changed. The darkness between those ghosts is not empty space. It is the present moment, unreachable and unseen. In the voids between galaxies, there are regions of space so empty that they contain almost nothing at all. These are called cosmic voids, and some of them are staggeringly large. The Boötes Void, discovered in 1981, spans approximately 330 million light-years across. Inside it, there are almost no galaxies. It is one of the largest known empty regions in the observable universe. Traveling through it at the speed of light would take over 300 million years, and during that entire journey, you might pass no more than 60 galaxies. For context, a similar volume of average space would contain thousands. The existence of cosmic voids is not a mystery in itself. The large-scale structure of the universe is like a vast cosmic web, with galaxies clustered along filaments and walls that surround enormous empty bubbles. This structure emerged from tiny density fluctuations in the early universe, amplified over billions of years by gravity. Where matter was slightly denser, it pulled in more matter and formed galaxies. Where it was slightly less dense, matter drained away, leaving behind the voids. The darkness inside a cosmic void is not the darkness of hidden light. It is genuine emptiness, as close to nothing as the universe gets. And yet even the voids are not truly empty. They contain thin wisps of hydrogen gas, stray photons from distant sources, and the ever-present cosmic microwave background radiation. They are also permeated by dark energy, the mysterious force that is causing the expansion of the universe to accelerate. In a sense, the voids are the purest expression of the universe's current state. They are what space looks like when matter has been pulled away and only the fundamental fabric remains. If you could stand inside a cosmic void and look outward, you would see the faintest possible scattering of distant galaxy light. It would be the darkest sky imaginable, and yet it would still not be perfectly black. Even there, the universe whispers. The cosmic microwave background radiation is arguably the most important glow in the history of science. It was first detected in 1965 by Arno Penzias and Robert Wilson, two radio astronomers working at Bell Labs in New Jersey. They were testing a large horn antenna designed for satellite communication when they noticed a persistent, low-level noise that they could not eliminate. It came from every direction in the sky. It did not change with the time of day or the season. It was always there, faint but constant, like a soft hum woven into the fabric of space itself. What Penzias and Wilson had stumbled upon was the afterglow of the Big Bang. Approximately 380,000 years after the birth of the universe, the cosmos had cooled enough for atoms to form. Before that moment, the universe was an opaque fog of free electrons and protons, so dense that photons could not travel freely. They scattered off particles almost immediately, like light inside a thick cloud. But when atoms formed, the fog cleared. Photons were suddenly free to travel across the universe unimpeded. That first flood of released light has been traveling ever since, cooling and stretching as the universe expanded, until today, it arrives as faint microwave radiation, with a temperature of just 2.725 degrees above absolute zero. This radiation fills the entire sky. It is not coming from any particular direction or any particular object. It is the remnant glow of the entire universe as it was 380,000 years after the Big Bang. When you tune a television to a channel with no signal and see static, roughly 1% of that static is caused by photons from the cosmic microwave background. You are literally watching the afterglow of creation on your television screen. NASA's COBE satellite, launched in 1989, was the first mission to map the cosmic microwave background with high precision. It confirmed that the radiation was almost perfectly uniform in every direction, with temperature variations of less than 1 part in 100,000. These tiny fluctuations, barely measurable, were the seeds of all structure in the universe. Regions that were slightly warmer were slightly denser, and over billions of years, gravity amplified those tiny differences into galaxies, galaxy clusters, and the entire cosmic web. The pattern of the cosmic microwave background is, in a very real sense, the blueprint of everything that exists. ESA's Planck satellite, launched in 2009, produced even more detailed maps of the cosmic microwave background. Its data allowed scientists to determine the age of the universe with extraordinary precision, to measure the rate of cosmic expansion, and to calculate the relative proportions of ordinary matter, and dark energy. According to Planck's measurements, ordinary matter, the atoms that make up stars, planets, and human beings, constitutes only about 4.9% of the total energy content of the universe. Dark matter accounts for about 26.8%, and dark energy accounts for approximately 68.3%. The vast majority of the universe is made of substances that are completely invisible and, so far, entirely undetectable by any direct means. The darkness of the night sky takes on a different meaning when you consider these numbers. It is not simply that distant starlight has been redshifted beyond visibility. It is that the stars and galaxies we can see represent less than 5% of what the universe actually contains. 95% of reality is dark. Not dark in the sense of being unlit, but dark in the sense of being unknown. We live in a universe where the vast majority of everything is invisible, intangible, and unexplained. The darkness we see when we look up is not just an optical phenomenon. It is a reflection of a deeper truth. Most of the universe is hidden from us in ways we are only beginning to understand. Dark matter was first proposed in the 1930s by the Swiss astronomer Fritz Zwicky. While studying the Coma Cluster, a massive collection of over 1,000 galaxies located about 320 million light-years away, Zwicky measured the velocities of the galaxies within the cluster. He found that they were moving far too fast. Based on the visible mass of the cluster, the galaxies should have been moving more slowly. At the speeds he observed, the cluster should have flown apart long ago. Something unseen was holding it together. Zwicky called this unseen substance dunkle Materie, dark matter. For decades, Zwicky's idea was largely ignored. It seemed too strange, an invisible substance that exerted gravitational influence but could not be seen, touched, or detected by any telescope. It sounded more like science fiction than science. But in the 1970s, the American astronomer Vera Rubin provided evidence so compelling that the scientific community could no longer look away. Rubin studied the rotation curves of spiral galaxies. In a spiral galaxy, stars orbit the galactic center much like planets orbit the sun. According to Newtonian gravity, stars at the outer edges of a galaxy should orbit more slowly than stars closer to the center, just as Neptune orbits the sun more slowly than Mercury. But when Rubin measured the orbital speeds of stars in the Andromeda galaxy and dozens of others, she found something astonishing. The stars at the outer edges were moving just as fast as those near the center. The rotation curves were flat. This was impossible unless there was far more mass in the galaxy than what could be seen. The visible stars and gas accounted for only a fraction of the gravitational pull required to explain the motion. Something massive, invisible, and spread throughout the galaxy was providing the rest. Today, the evidence for dark matter is overwhelming and comes from multiple independent sources. Galaxy rotation curves, gravitational lensing, the cosmic microwave background, the large-scale structure of the universe, and the dynamics of galaxy clusters all point to the same conclusion. There is roughly 5 times more dark matter in the universe than ordinary matter. It does not emit light. It does not absorb light. It does not interact with the electromagnetic force at all. It passes through ordinary matter as if it were not there. The only way we know it exists is through its gravitational effects on the things we can see. The nature of dark matter remains one of the greatest unsolved problems in physics. Scientists have proposed dozens of candidate particles, from weakly interacting massive particles, known as WIMPs, to ultralight axions, to sterile neutrinos. Underground laboratories around the world, shielded from cosmic rays by kilometers of rock, have been searching for dark matter particles for decades. The Xenon 1T experiment in Italy, the LUX Zeppelin experiment in South Dakota, and the Pandex experiment in China have all pushed the limits of detection to extraordinary sensitivity. So far, not a single dark matter particle has been directly detected. Whatever dark matter is, it is profoundly elusive. It shapes the structure of the universe, holds galaxies together, and outweighs all the stars and planets combined. Yet it has never been captured, contained, or identified. There is a technique called gravitational lensing that allows astronomers to see the influence of dark matter directly. When light from a distant galaxy passes near a massive object, such as a galaxy cluster, the gravity of that object bends the path of the light, just as a glass lens bends a beam of light. If the mass is large enough, it can distort the images of background galaxies into arcs, rings, and multiple copies. By measuring the degree of distortion, astronomers can map the distribution of mass in the foreground object, including the mass that is invisible. When they do this, they find that the visible galaxies account for only a small fraction of the total mass. The rest is dark matter, forming a vast invisible scaffold around which the visible universe is draped. One of the most striking demonstrations of dark matter comes from the Bullet Cluster, a pair of galaxy clusters that collided roughly 150 million years ago. When the two clusters smashed into each other, their hot gas, which makes up most of the ordinary matter in galaxy clusters, slowed down and piled up in the middle, like two clouds of steam colliding. But the dark matter, which does not interact with ordinary matter or even with itself, passed straight through. Observations using gravitational lensing showed that the mass of each cluster had separated from its gas. The dark matter had sailed ahead while the gas lagged behind. This separation provided direct, visual proof that dark matter is real, that it behaves differently from ordinary matter, and that it constitutes the majority of the mass in these enormous structures. In the early universe, dark matter played a crucial role in the formation of galaxies. After the Big Bang, the universe was almost perfectly smooth. The tiny density fluctuations visible in the cosmic microwave background were the only irregularities. Ordinary matter alone could not have collapsed fast enough under gravity to form galaxies by the time we observe them. But dark matter, which does not interact with light and therefore was not affected by the pressure of radiation in the early universe, began clumping together much earlier. It formed a web of invisible scaffolding, a vast network of dark matter halos. When ordinary matter finally decoupled from radiation, 380,000 years after the Big Bang, it fell into these preformed dark matter wells. The galaxies we see today formed within cradles of dark matter. Every galaxy, including our own Milky Way, sits inside a massive halo of dark matter that extends far beyond its visible edges. The Milky Way's dark matter halo is estimated to extend roughly 300,000 light-years from the galactic center, far beyond the visible disk of stars, which spans about 100,000 light-years. The total mass of the dark matter halo is estimated to be about 1 trillion solar masses, roughly 10 times the mass of all the stars in the galaxy combined. We are embedded in a vast, invisible sphere of matter that we cannot see, cannot touch, and cannot directly detect. It surrounds us in every direction. It passes through the room you are in right now. Every second, billions of dark matter particles may be streaming through your body without interacting with a single atom. You would never know. The search for dark matter has led scientists to build some of the most sensitive instruments ever conceived. Deep underground, in laboratories carved into mountains and abandoned mines, detectors wait in silence for the faintest possible signal. The principle is simple. If a dark matter particle were to collide with an atom of xenon, argon, or another target material, it would produce a tiny flash of light or a minute vibration. The detectors are designed to register these impossibly faint events. But the background noise from cosmic rays, radioactive decay, and even the natural radioactivity of the detector materials themselves is far greater than the expected signal. To reduce this noise, the experiments are buried deep underground, surrounded by layers of shielding and cooled to cryogenic temperatures. Despite decades of effort and extraordinary technological achievement, no experiment has yet made a confirmed direct detection of a dark matter particle. Each null result eliminates another region of the possible parameter space, narrowing the range of properties that dark matter could have. But the mystery endures. Dark matter continues to reveal itself only through gravity, shaping the universe on the largest scales while remaining stubbornly invisible on every other level. It is the most abundant form of matter in the cosmos, and we do not know what it is. There is something called the dark matter web. Computer simulations of the universe's evolution, run on some of the most powerful supercomputers in the world, have shown that dark matter is not distributed randomly through space. It forms a vast, three-dimensional network of filaments, sheets, and nodes. The filaments stretch across hundreds of millions of light years, connecting galaxy clusters like threads in a cosmic spider's web. At the nodes where filaments intersect, the densest concentrations of dark matter are found, and these are where the largest galaxy clusters reside. Between the filaments are the cosmic voids, enormous bubbles of near emptiness where dark matter is sparse and galaxies are rare. This structure is called the cosmic web, and it is the largest pattern in the known universe. It was predicted by computer simulations before it was observed, and when astronomers mapped the distribution of galaxies on the largest scales, they found exactly the web-like structure the simulations had predicted. The galaxies trace the filaments. The voids are real. The universe has structure on scales so vast that the human mind struggles to comprehend them. And the invisible skeleton of that structure, the framework upon which everything visible is built, is dark matter. While dark matter provides the gravitational scaffolding for the universe, another form of darkness operates on an even grander scale. Dark energy is the name given to the mysterious force that is causing the expansion of the universe to accelerate. It was discovered in 1998 by two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, who were studying distant type Oertz supernovae to measure the rate at which the expansion of the universe was slowing down. They expected to find that gravity, pulling on all the matter in the universe, was gradually decelerating the expansion, like a ball thrown upward that slowly loses speed. Instead, they found the opposite. The expansion was not slowing down. It was speeding up. This discovery was so unexpected, so contrary to everything physicists thought they understood, that it was initially met with disbelief. The data was checked and rechecked. Independent observations confirmed the result. The universe was accelerating. Something was pushing it apart, something with enough energy to overpower the combined gravity of all the matter in the cosmos. That something was given the name dark energy, though the name is a placeholder more than a description. We do not know what dark energy is. We do not know where it comes from. We do not know why it has the strength it does. We only know that it exists, that it fills all of space, and that it is the dominant force shaping the future of the universe. The discovery of the accelerating expansion of the universe earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. Their work overturned the assumption that gravity would eventually slow and perhaps reverse the expansion of the universe. Instead, the universe appears destined to expand forever, faster and faster, until the most distant galaxies are carried beyond our cosmic event horizon and vanish from view. Dark energy accounts for approximately 68.3% of the total energy content of the universe, according to measurements from ESA's Planck satellite. This makes it by far the dominant component of reality, and yet it is the least understood. It does not clump like matter. It does not form structures. It appears to be a property of space itself, a constant energy density that permeates every cubic centimeter of the void. As the universe expands and the volume of space increases, the total amount of dark energy increases with it. This is deeply counterintuitive. In every other context we know of, energy is conserved. But dark energy seems to be created out of nothing as space itself grows. One leading hypothesis is that dark energy is the energy of the vacuum. Quantum mechanics tells us that even empty space is not truly empty. It is filled with a roiling sea of virtual particles, constantly popping into existence and annihilating each other in durations so short they cannot be directly observed. This quantum vacuum has energy, and that energy could, in principle, exert a repulsive gravitational effect that drives the expansion of space. The problem is that when physicists calculate the expected energy of the quantum vacuum, using the standard methods of quantum field theory, the answer they get is roughly 10 to the power of 120 times larger than the observed value of dark energy. This is the largest discrepancy between theory and observation in the history of physics, and it has been called the worst prediction ever made by a scientific theory. Something is deeply wrong with our understanding of the vacuum, and dark energy sits at the center of that mystery. Another possibility is that dark energy is not constant, but changes over time. A varying dark energy, sometimes called quintessence, would behave differently from a cosmological constant, and could have been weaker or stronger at different epochs in the universe's history. Several experiments are currently underway to test this idea, including the Dark Energy Survey, the European Space Agency's Euclid mission launched in 2023, and NASA's Nancy Grace Roman Space Telescope. These missions aim to map the distribution of galaxies and dark matter across billions of light years and measure how the expansion rate of the universe has changed over time. If dark energy varies, these measurements should be able to detect it. There is yet another possibility, one that some physicists find both exciting and unsettling. Perhaps dark energy is not a substance or a field at all. Perhaps it is a sign that our theory of gravity, general relativity, is incomplete. Einstein's equations describe gravity with extraordinary precision in most circumstances, but they have never been tested on the largest cosmic scales with the accuracy needed to rule out modifications. Some modified gravity theories can reproduce the observed acceleration of the universe without invoking dark energy. If one of these theories is correct, then the darkness of the universe is not caused by an invisible energy filling space. It is caused by gravity itself behaving differently than we expect on the grandest scales. The darkness would not be a thing. It would be a clue that our understanding of the fundamental forces is still missing something. The cosmological constant, represented by the Greek letter lambda, was first introduced by Albert Einstein in 1917. At the time, the prevailing belief was that the universe was static, neither expanding nor contracting. But Einstein's equations of general relativity predicted a dynamic universe, one that would either expand or collapse under its own gravity. To prevent this, Einstein added the cosmological constant as a counterbalancing term, a kind of repulsive force that would hold the universe in perfect equilibrium. When Hubble discovered the expansion of the universe in 1929, Einstein reportedly called the cosmological constant his greatest blunder and abandoned it. Decades later, the discovery of the accelerating expansion brought the cosmological constant back. If dark energy behaves as a constant energy density, it is mathematically equivalent to Einstein's lambda. The term he introduced to keep the universe still may turn out to describe the force that is tearing it apart. It is one of the most remarkable reversals in the history of science. Einstein was wrong about the universe being static, but the mathematical tool he invented to support that wrong idea may be the correct description of the force that dominates the cosmos. The interplay between dark matter and dark energy defines the large-scale fate of the universe. Dark matter pulls things together. Dark energy pushes them apart. For the first several billion years after the Big Bang, dark matter dominated, and gravity caused the universe to form structures, galaxies, clusters, and the cosmic web. But roughly 5 billion years ago, dark energy began to win. The expansion started accelerating. Structures stopped growing. The cosmic web is now slowly being stretched apart, and in the far future, the spaces between galaxy clusters will grow so vast that they will become causally disconnected, unable to communicate or interact. If dark energy remains constant, the long-term future of the universe is one of increasing isolation. Galaxy clusters will drift apart. The night sky, already dark, will grow darker. In the far, far future, trillions of years from now, an observer in the Milky Way, which by then will have merged with the Andromeda Galaxy, will look out and see nothing. Every other galaxy will have been carried beyond the cosmic event horizon. The cosmic microwave background will have been redshifted to wavelengths so long that it becomes undetectable. The universe will appear to contain only one galaxy, alone in an infinite void. The evidence that the Big Bang ever happened, that other galaxies ever existed, that the universe was once young and hot and dense, will have been erased by expansion. The darkness will be not just physical, but epistemic. The universe will have hidden its own history. There is a form of darkness that is not cosmic, but deeply local. Every object in the solar system casts a shadow, and those shadows extend outward into space in long, tapering cones. The shadow of the Earth, called the umbra, stretches about 1.4 million kilometers into space, roughly 3.5 times the distance to the Moon. When the Moon passes through this shadow, we see a lunar eclipse. The shadow of Jupiter is so large that several of its moons regularly pass through it, briefly vanishing from the sunlight before emerging again on the other side. Shadows are places where light has been blocked, and in the vacuum of space, they are sharp-edged and absolute. There is no atmosphere to scatter light into them. The boundary between light and shadow in space is crisp, sudden, and total. On the Moon, the shadows are among the deepest in the solar system. Because the Moon has no atmosphere, there is no scattered light to soften the darkness. When an astronaut steps behind a boulder on the lunar surface, the shadow is pitch black. The Apollo astronauts reported that they could not see their own hands in the shadows, even in the brightness of lunar day. The contrast between sunlight and shadow on the moon is extreme, more extreme than anything experienced on Earth. And at the lunar poles, there are craters so deep and so angled that sunlight has not reached their floors in billions of years. These permanently shadowed regions are among the coldest places in the solar system, with temperatures dropping below minus 240 degrees Celsius. NASA's Lunar Reconnaissance Orbiter has mapped these frozen shadows in detail, and scientists believe they may contain water ice, delivered by comets over billions of years and preserved in the eternal cold. The darkness of these craters has kept their contents frozen since before the dinosaurs existed. In the outer solar system, darkness is not an exception. It is the rule. Beyond the orbit of Mars, sunlight fades rapidly. At Jupiter, the sun appears as a small, bright disk, only 1/27 the size it appears from Earth. At Saturn, it is even smaller. At Neptune, nearly 4.5 billion kilometers from the sun, sunlight is roughly 900 times fainter than it is on Earth. A sunny day on Neptune would appear to human eyes like deep twilight. And beyond Neptune, in the Kuiper Belt and the Oort cloud, the sun dwindles to little more than a bright star. The outer solar system is a realm of permanent dusk, where the sun's warmth and light are faint memories of a distant inner world. The space between stars is not empty. It is filled with a thin, cold medium called the interstellar medium, composed mostly of hydrogen gas and tiny grains of dust. This material is extraordinarily sparse, with an average density of about 1 atom per cubic centimeter, a vacuum far more perfect than anything achievable in a laboratory on Earth. But over the vast distances between stars, even this thin material adds up. Interstellar dust absorbs and scatters starlight, dimming and reddening the light from distant stars. In regions where the dust is particularly dense, it can block visible light entirely, creating dark patches against the backdrop of the Milky Way. These dark patches were once called dark nebulae, and early astronomers believed they were holes in the sky, windows into the empty void beyond the stars. The astronomer William Herschel, observing a particularly prominent dark region in the constellation Scorpius in the late 18th century, reportedly exclaimed that he had found a hole in the heavens. He was wrong. The darkness was not an absence of stars. It was a presence of dust. Behind the dark nebula, the stars continued, shining as brightly as ever, but their light was being absorbed by the dense cloud of interstellar material between them and Earth. One of the most beautiful dark nebulae in the sky is called the Horsehead Nebula, located in the constellation Orion. It appears as a dark silhouette shaped roughly like the head and neck of a horse, set against a glowing background of red hydrogen gas. The Horsehead is a dense cloud of dust and cold gas, about 1,500 light-years from Earth, and it is a stellar nursery. Deep within its dark folds, new stars are forming. The darkness of the Horsehead is not emptiness, it is potential. It is the raw material of future solar systems, future planets, perhaps even future life. The blackest regions of the nebula are where the next generation of stars is being born. There is a structure in the constellation Ophiuchus called the Dark River, a long, winding lane of interstellar dust that stretches across the sky like a river of shadow. It is not truly a river, of course. It is a filament of dense gas and dust, part of the Ophiuchus molecular cloud complex, one of the nearest regions of active star formation to Earth. The Dark River is about 500 light-years away and several hundred light-years long. Behind it, thousands of stars shine, but their light is swallowed by the dust before it reaches our eyes. The river flows in darkness, not because it is empty, but because it is full of the cold, dense material from which new stars will someday ignite. The darkest material in the solar system is found on the surface of certain comets and asteroids. Comet 67P Churyumov-Gerasimenko, studied in extraordinary detail by ESA's Rosetta mission from 2014 to 2016, has a surface darker than charcoal. It reflects only about 6% of the sunlight that hits it. If you could hold a piece of this comet's surface in your hand, it would appear almost black. The darkness comes from a coating of complex organic molecules, carbon-rich compounds that absorb nearly all incoming light. Similar dark coatings have been found on asteroids in the outer solar system, particularly those in the Trojan groups that share orbits with Jupiter. These objects are among the darkest in the known solar system, remnants of the cold, carbon-rich material from which the planets formed billions of years ago. There is an asteroid called Bennu that was visited by NASA's OSIRIS-REx spacecraft in 2018. Bennu is a near-Earth asteroid roughly 500 meters across, and its surface is strikingly dark, reflecting only about 4% of the light that reaches it. The spacecraft collected a sample of Bennu's surface material and returned it to Earth in September 2023. Analysis of the sample revealed abundant water-bearing minerals, organic compounds, and minerals that had formed in the presence of liquid water early in the solar system's history. The darkness of Bennu's surface tells a story of ancient chemistry, of carbon-rich materials that predate the formation of the planets, preserved in the cold and dark of space for over 4 billion years. The night side of a planet is a special kind of darkness. When a planet rotates, the hemisphere facing away from the sun enters shadow. On Earth, this shadow is the night. But on other worlds, the night is very different. On Venus, the thick atmosphere traps heat so effectively that the night side is almost as hot as the day side, with surface temperatures around 460 degrees Celsius, regardless of whether the sun is shining. On Mars, the thin atmosphere means the night side cools rapidly, with temperatures dropping by 70 degrees or more between day and night. On the gas giants, there is no solid surface for darkness to fall upon. The night side of Jupiter is a realm of swirling cloud patterns dimly lit by auroral glow and internal heat. Jupiter radiates more energy than it receives from the sun, so even its night side is not truly cold. It glows faintly with its own inner warmth. Saturn's moon, Enceladus, presents one of the most remarkable examples of darkness hiding something extraordinary. Enceladus is a small, icy moon, only about 500 kilometers across. Its surface is covered in fresh, bright ice that reflects nearly all the sunlight that hits it, making it one of the most reflective objects in the solar system. But at its south pole, hidden in shadow for part of its orbit, enormous geysers of water vapor and ice particles erupt from fractures in the ice called tiger stripes. NASA's Cassini spacecraft, which studied Saturn and its moons from 2004 to 2017, flew through these plumes and detected water, organic molecules, and molecular hydrogen. Ingredients that, on Earth, are associated with hydrothermal vents at the bottom of the ocean where life thrives. Beneath the dark, icy surface of Enceladus, there is a global ocean of liquid water. In the darkness beneath the ice, conditions may exist that could support life. Jupiter's moon. Europa is another world where darkness conceals possibility. Europa's surface is a shell of ice, crisscrossed with dark streaks and ridges that suggest tectonic activity driven by the tidal forces of Jupiter's gravity. Beneath this ice shell, scientists believe there is a vast ocean of liquid water, containing perhaps 2 to 3 times as much water as all of Earth's oceans combined. The ocean is kept liquid by the tidal heating caused by Jupiter's enormous gravitational pull, which flexes and warms Europa's interior. NASA's Europa Clipper mission, launched in October 2024, is on its way to study this moon in detail. searching for evidence of the conditions necessary for life. The darkness beneath Europa's ice may hide the most important ocean in the solar system. In the deepest parts of Earth's own oceans, there is a kind of darkness that mirrors the cosmic void. Below about 1,000 meters, no sunlight penetrates. This region is called the aphotic zone, and it makes up the vast majority of the ocean's volume. The pressure is crushing. The temperature hovers just above freezing, and yet this darkness is teeming with life. Bioluminescent organisms produce their own light, creating flashes and glows in the abyss. Anglerfish dangle luminous lures. Jellyfish pulse with blue and green light. Squid flash patterns of color for communication and camouflage. In the deepest darkness on Earth, life has not retreated. It has invented its own light. At hydrothermal vents on the ocean floor, superheated water, rich in minerals, pours from cracks in the Earth's crust at temperatures exceeding 400 degrees Celsius. Where this water meets the near-freezing deep ocean, minerals precipitate out, forming towering chimney structures called black smokers. The water that billows from these chimneys is dark with dissolved minerals, giving them their name. Around these vents, entire ecosystems thrive in total darkness, powered not by sunlight, but by chemical energy. Giant tube worms, ghostly white crabs, and dense mats of bacteria form communities that owe nothing to the sun. These ecosystems were among the most surprising discoveries of the 20th century, proof that life does not require light to flourish. Darkness, it turns out, is not hostile to life. It is simply a different kind of home. The color of the universe, averaged across all the light from all the galaxies, has been calculated. In 2002, astronomers Carl Glazebrook and Ivan Baldry at Johns Hopkins University averaged the light from over 200,000 galaxies observed by the 2DF Galaxy Redshift Survey. They found that the average color of the universe is a pale beige, which they named cosmic latte. It is the color you would see if you could blend all the starlight in the observable universe into a single hue. In the past, when the universe was younger and forming stars more vigorously, its average color was bluer. As star formation has slowed and older, redder stars have come to dominate. The universe has gradually been reddening. Cosmic latte is not the color of darkness. It is the color of all the light the universe has ever made, mixed together. The darkness of the sky is what remains when that light is too faint and too spread out to see. There is a phenomenon called the Gegenschein, or counterglow, that is visible under exceptionally dark skies. It appears as a faint, oval patch of light directly opposite the sun's position in the sky, centered on the anti-solar point. It is caused by sunlight reflecting off interplanetary dust particles that lie along the plane of the solar system. These particles are remnants of comets and asteroid collisions, and they form a thin disk of dust that extends throughout the inner solar system. The Gegenschein is so faint that it can only be seen from locations far from artificial light on clear, moonless nights. It is a reminder that even the darkest skies are not perfectly black. The solar system is filled with a faint, scattered haze of reflected sunlight, a gentle dust glow that is one of the most subtle phenomena visible to the naked eye. A related phenomenon is the zodiacal light, a faint pyramid of light that rises from the horizon shortly after sunset or before sunrise. Like the Gegenschein, it is caused by sunlight scattering off interplanetary dust. The zodiacal light can be quite prominent in tropical regions where the ecliptic makes a steep angle with the horizon. It was known to ancient observers and was sometimes called the false dawn. In extremely dark conditions, the zodiacal light can be traced all the way across the sky, connecting with the Gegenschein in a continuous band of faint light called the zodiacal band. This entire structure is the sun's dusty fingerprint, a reminder that our star illuminates not just the planets, but the vast cloud of debris that fills the spaces between them. The human eye is an extraordinary detector of light, but it has limits that shape our perception of the darkness of the sky. In bright conditions, the eye uses cone cells, which are sensitive to color but require relatively strong light. In darkness, the eye switches to rod cells, which are far more sensitive but detect only shades of gray. It takes about 20 to 30 minutes for the eye to fully adapt to darkness, a process called dark adaptation. During this time, the chemical rhodopsin builds up in the rod cells, increasing their sensitivity by a factor of roughly 10,000. A fully dark-adapted human eye can detect a single candle flame from about 1.6 miles away. It can see stars down to roughly magnitude 6, which corresponds to about 9,000 individual stars visible across the entire sky from a single location. But even a fully dark-adapted eye under perfect conditions sees only a fraction of what is out there. The Milky Way contains an estimated 200 to 400 billion stars, and we can see fewer than 10,000 of them. The faintest visible stars are those with magnitudes around 6.0, but the sky is filled with stars too faint for the eye to detect, blending into a diffuse glow that contributes to the overall brightness of the sky without being visible as individual points. This unresolved starlight is called the diffuse galactic light, and it is one of the reasons the Milky Way appears as a glowing band rather than a collection of individual stars. The darkness between the visible stars is not empty. It is filled with stars too faint to see, their combined light forming a gentle, invisible glow. Light pollution is the modern enemy of darkness. In cities, streetlights, building illumination, signs, and vehicles scatter light into the atmosphere, creating a glowing dome called sky glow that washes out the stars. A study published in 2016 in the journal Science Advances found that more than 80% of the world's population lives under light-polluted skies. In the United States and Europe, the figure is over 99%. 1/3 of humanity can no longer see the Milky Way from where they live. The darkest skies on Earth are now found in remote deserts, high mountains, and oceanic islands far from any human settlement. For most of human history, the full glory of the night sky was visible to anyone who looked up. Today, it has become a rare and precious sight. The loss of true darkness has consequences beyond astronomy. Artificial light at night disrupts the circadian rhythms of humans and wildlife alike. Migratory birds become disoriented by city lights and crash into illuminated buildings. Sea turtle hatchlings, which navigate toward the ocean by the light of the moon reflecting off the water, are drawn inland by coastal lighting and die of exhaustion and dehydration. Insects are attracted to artificial lights in vast numbers, disrupting pollination, food webs, and predator-prey relationships. In humans, exposure to artificial light at night suppresses the production of melatonin, a hormone that regulates sleep and has been linked to protection against certain cancers. The darkness of night is not just an aesthetic treasure. It is a biological necessity, woven into the physiology of nearly every living thing on Earth. There are efforts underway to protect the remaining dark skies. The International Dark Sky Association certifies locations that meet strict criteria for darkness and lighting management as international dark sky parks and reserves. These include places like Natural Bridges National Monument in Utah, the Aoraki Mackenzie International Dark Sky Reserve in New Zealand, and the island of Sark in the Channel Islands, which became the world's first dark sky island in 2011. In these protected places, the Milky Way arches overhead in full glory, and thousands of stars are visible to the naked eye. Visitors often describe the experience as life-changing, a reconnection with a sky that most people have never seen. The Bortle scale is a 9-level system for measuring the darkness of the night sky, developed by amateur astronomer John Bortle in 2001. A Bortle Class 1 sky is the darkest possible, found only in the most remote locations on Earth. Under a Class 1 sky, the zodiacal light is prominent, the Gegenschein is clearly visible, the Milky Way casts visible shadows on the ground, and the sky is so dark that the eye's own imperfections become visible as faint patterns called entoptic phenomena. A Bortle Class 9 sky is the brightest, found in the centers of major cities, where only the moon, planets, and a handful of the brightest stars are visible. The difference between these two extremes is staggering. A person who has only ever lived under a Class 7 or 8 sky has never seen the real night sky. They have seen a dim, washed-out approximation of it. The speed of light is the reason the night sky is also a time machine. When you look at the star Sirius, the brightest star in the night sky, you are seeing it as it was about 8.6 years ago, because that is how long its light takes to reach Earth. When you look at the Andromeda Galaxy, the most distant object visible to the naked eye, you are seeing it as it was about 2.5 million years ago. The light arriving at your eyes tonight left Andromeda when early humans were just beginning to walk upright on the plains of Africa. Every star you see is a window into the past, and the deeper you look, the further back in time you travel. The darkness between the stars is not just empty space, it is the present, the one thing the sky cannot show you. There is a theory in cosmology called the Big Freeze, or heat death, which describes the ultimate fate of the universe if dark energy continues to drive accelerating expansion. In this scenario, the universe continues to expand forever. Galaxies drift apart. Stars burn through their fuel and die. The last red dwarf stars, the smallest and longest lived, will finally exhaust their hydrogen fuel in about 100 trillion years. After that, the universe will contain only stellar remnants, white dwarfs, neutron stars, and black holes. Over unimaginably long timescales, even these will fade. White dwarfs will cool to black dwarfs, objects so cold they emit no detectable radiation. Neutron stars will follow, and eventually, even black holes will evaporate through a process called Hawking radiation, discovered theoretically by Stephen Hawking in 1974. The timescale for a stellar mass black hole to evaporate is roughly 10 to the power of 67 years. For a supermassive black hole, the timescale is on the order of 10 to the power of 100 years, a Google years. After the last black hole has evaporated, the universe will consist of nothing but a thin, cooling sea of photons, neutrinos, and perhaps a few scattered subatomic particles, all drifting ever further apart in an ever-expanding void. The temperature of the universe will asymptotically approach absolute zero, but never quite reach it. This is the heat death, the state of maximum entropy, where no energy gradients exist to drive any process, no work can be done, and nothing ever happens again. In this far future, the universe will be dark in the most complete sense imaginable. Not dark because light has been redshifted. Not dark because dust is in the way. Not dark because the eye cannot detect faint photons. Dark because there is nothing left to produce light. The last photons will stretch to wavelengths longer than the observable universe itself, becoming so tenuous that they cease to have any physical meaning. The darkness will be total, eternal, and absolute. It is a future so remote that the current age of the universe, 13.8 billion years, is essentially the first instant of cosmic morning. But there is another possibility, stranger and more violent. If dark energy is not constant but increases in strength over time, a scenario called the Big Rip could unfold. In a Big Rip scenario, the repulsive force of dark energy grows stronger and stronger, eventually overpowering not just gravity, but all the forces that hold matter together. First, galaxy clusters would be torn apart, then individual galaxies, then solar systems, then planets, then atoms themselves. In the final moments, the fabric of space-time would be ripped apart, and the universe would end not in a slow fade, but in a sudden, violent dissolution. Current observations suggest that a Big Rip is unlikely, as dark energy appears to be very close to constant. But the possibility has not been entirely ruled out. The darkness of the future may be gentle, or it may be cataclysmic. We do not yet know. There is something profoundly beautiful about the fact that we exist in the brief window of cosmic history when the universe is lit. Stars have been burning for only about 13 billion years. They will continue for perhaps another 100 trillion. But on the full timeline of the universe, from the Big Bang to the heat death, the era of starlight is a fleeting flash. Almost all of cosmic time will be dark. We are living in the light. Every star we see, every galaxy we photograph, every sunset we watch is part of a temporary, transient illumination in an overwhelmingly dark cosmos. The night sky is dark, yes. But it is dark the way a room is dark when a candle has just been lit. The darkness is real, but so is the light. And the light is right now. Neutron stars are among the densest objects in the universe, and their darkness is of a peculiar kind. A neutron star is the collapsed core of a massive star that has exploded as a supernova. It packs roughly 1.5 times the mass of the Sun into a sphere only about 20 kilometers across. The density is almost inconceivable. A sugar cube-sized piece of neutron star material would weigh about 1 billion tons on Earth. When a neutron star first forms, it is extraordinarily hot, with surface temperatures exceeding 1,000,000 degrees Celsius. It glows brightly in X-rays, but over millions of years, it cools. As it cools, it fades. Old neutron stars become nearly invisible, radiating only faint thermal emissions. They are still there, drifting through the galaxy, carrying a mass greater than the Sun in a space smaller than a city, but they have gone dark. The galaxy is filled with these invisible remnants, cold and silent, marking the graves of stars that burned out long ago. Black holes represent the ultimate form of cosmic darkness. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. The boundary of a black hole is called the event horizon, and it is not a physical surface, but a mathematical boundary. Once anything crosses the event horizon, it is gone from the observable universe forever. No signal, no light, no information can return from beyond that boundary. The interior of a black hole is, by definition, invisible. It is the most complete form of darkness that physics allows, and yet black holes are not entirely dark. The matter falling into a black hole does not simply vanish. Before it crosses the event horizon, it spirals inward through a structure called an accretion disk, a swirling platter of superheated gas that emits enormous amounts of radiation, including visible light, ultraviolet, and X-rays. The accretion disks of supermassive black holes at the centers of galaxies can outshine the entire galaxy itself, producing more light than 100 billion stars combined. These objects are called active galactic nuclei or quasars, and they are among the brightest objects in the universe. The darkest objects in existence are surrounded by the most brilliant light. In April 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow. The target was the supermassive black hole at the center of the galaxy M87, a giant elliptical galaxy in the constellation Virgo. The black hole has a mass of about 6.5 billion times that of the Sun. The image showed a bright ring of light surrounding a dark central region, the shadow of the event horizon. The light in the ring was produced by the superheated gas in the accretion disk, bent and magnified by the black hole's extreme gravity. The dark center was the event horizon itself, the boundary beyond which light cannot escape. It was the first time humanity had ever seen the shape of pure gravitational darkness. In May 2022, the Event Horizon Telescope released a second image, this time of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. Sagittarius A star has a mass of about 4 million solar masses and sits approximately 26,000 light-years from Earth. Despite being much smaller than the M87 black hole, Sagittarius A star presented greater imaging challenges because the gas around it moves much faster relative to its size, causing the image to flicker and change rapidly. The final image, constructed from multiple observations, again showed the telltale ring of light and dark shadow. At the heart of our galaxy, at the center of the spiral of stars that we call home, there is a region of absolute darkness, and we have now seen its outline. Gravitational waves are ripples in the fabric of space-time caused by the acceleration of massive objects. They were predicted by Einstein's general theory of relativity in 1916, but not directly detected until 2015, when the LIGO observatories in Louisiana and Washington state recorded the gravitational waves produced by the merger of two black holes roughly 1.3 billion light-years away. The signal lasted less than a second. In that brief moment, the two black holes, each about 30 times the mass of the Sun, spiraled together and merged into a single, larger black hole. The energy released in gravitational waves was equivalent to about 3 solar masses, converted entirely into energy. More power than all the stars in the observable universe were producing at that instant. And yet, because gravitational waves interact so weakly with matter, the signal that reached Earth was almost impossibly faint, a stretching of space smaller than 1,000th the width of a proton. Since that first detection, LIGO and its partner observatory Virgo in Italy have detected dozens of gravitational wave events, including mergers of neutron stars, mergers of black holes and neutron stars, and the largest black hole mergers ever observed. Each event is a moment when invisible objects in the dark universe collide, producing ripples that travel across billions of light-years and arrive at Earth as barely perceptible whispers in the fabric of space. Gravitational wave astronomy has opened a new way of observing the universe, one that does not rely on light at all. It is a way of listening to the darkness. There is a kind of radiation called the cosmic neutrino background that fills the entire universe, even more ancient than the cosmic microwave background. Neutrinos are ghostly particles with almost no mass and almost no interaction with matter. They were produced in enormous numbers in the first seconds after the Big Bang, roughly 1 second after the beginning of time, when the universe was still a seething cauldron of particles and radiation. These primordial neutrinos have been traveling through space ever since, cooling as the universe expands, and they now have a temperature of roughly 1.95 degrees above absolute zero. They fill every cubic centimeter of the universe. Hundreds of billions of them pass through your body every second, but they are so weakly interacting that detecting them directly is currently beyond our technological ability. The cosmic neutrino background is one of the oldest forms of darkness in the universe, a sea of invisible particles that have been traveling since before atoms existed. There is a limit to how far back in time we can see using light. The cosmic microwave background represents a wall, the surface of last scattering, beyond which the universe was opaque. Before atoms formed 380,000 years after the Big Bang, photons could not travel freely. They were trapped in a fog of free electrons and protons. We cannot see beyond this wall using electromagnetic radiation of any kind. Everything before that moment is hidden from us. But neutrinos and gravitational waves, both of which were produced even earlier and which interact far more weakly with matter, could in principle carry information from those earliest moments. If we could detect the cosmic neutrino background or primordial gravitational waves with sufficient precision, we could peer behind the wall of light and glimpse the universe as it was in its first seconds and minutes. The darkness before the cosmic microwave background is not a void. It is a treasure vault of information, locked behind the limits of our current technology. There is a period in cosmic history called the Dark Ages. It lasted from about 380,000 years after the Big Bang, when the cosmic microwave background was released, to roughly 200 million years later, when the first stars began to form. During this period, the universe contained no stars, no galaxies, and no sources of visible light. It was filled with neutral hydrogen gas, slowly cooling in the expanding darkness. The cosmic microwave background was still glowing, but it was rapidly redshifting from visible light into the infrared and then the microwave part of the spectrum. The universe was, for this extended period, genuinely dark. No structure had yet formed. No light was being produced. The raw materials for stars existed, distributed in faint density fluctuations across the cosmic web, but they had not yet collapsed under gravity to ignite nuclear fusion. The cosmos was a vast, silent, lightless expanse waiting for the first spark. The end of the Dark Ages is called cosmic dawn, the moment when the first stars ignited and began to illuminate the universe. These first stars, called population 3 stars, are believed to have been enormous, perhaps hundreds of times the mass of the Sun, and extraordinarily luminous. They formed from pristine hydrogen and helium, the only elements that existed before stellar nucleosynthesis began. Because they contained no heavier elements, they burned hot, fast, and bright, flooding their surroundings with ultraviolet radiation that began to ionize the neutral hydrogen gas, creating expanding bubbles of ionized gas in the surrounding darkness. This process is called cosmic reionization, and it gradually transformed the universe from a dark, neutral fog into the transparent, ionized cosmos we observe today. The James Webb Space Telescope was designed in part to observe the earliest galaxies and stars, pushing back toward the edge of cosmic dawn. In its first year of operations, JWST detected galaxies that appear to have formed within the first few hundred million years after the Big Bang, earlier than many models had predicted. Some of these galaxies are surprisingly bright and massive for their age, challenging existing theories of galaxy formation. They are glimpses of the universe in its earliest stages of illumination, the first islands of light in a sea of primordial darkness. There is a signal that astronomers hope to detect from the Dark Ages themselves. Neutral hydrogen emits and absorbs radiation at a specific wavelength of 21 centimeters, corresponding to a transition between two energy states of the hydrogen atom. This 21-centimeter signal from the Dark Ages, red-shifted by the expansion of the universe to wavelengths of several meters, could in principle be detected by specially designed radio telescopes. Projects like the Hydrogen Epoch of Reionization Array, known as HERA, and the Future Square Kilometer Array, are working toward detecting this faint signal. If they succeed, it would open a window into the one period of cosmic history we have never observed directly, the era when the universe was truly dark. The observable universe has a shape, and that shape has been measured. Data from ESA's Planck satellite and other sources indicate that the observable universe is very close to geometrically flat. This means that the rules of Euclidean geometry apply on the largest scales. Parallel lines remain parallel. The angles of a triangle add up to 180 degrees. The flatness of the universe is related to its total energy density, which appears to be very close to the critical density, the exact value at which the universe is flat. If the density were slightly higher, the universe would be positively curved, like the surface of a sphere, and would eventually collapse. If slightly lower, it would be negatively curved, like a saddle, and would expand forever at an increasing rate. The flatness of the universe is one of the key observations that led to the theory of cosmic inflation, a period of exponentially rapid expansion in the first tiny fraction of a second after the Big Bang, which would have smoothed out any curvature and driven the geometry toward perfect flatness. The flatness of the universe also relates to its darkness in a subtle way. A perfectly flat universe with the critical density is one that expands forever, but at an ever-decreasing rate, approaching but never reaching a halt in the absence of dark energy. With dark energy, the expansion accelerates, and the universe expands faster and faster. In either case, the expansion ensures that the universe will never recollapse into a dense, hot, bright state. The darkness of the future is built into the geometry of space itself. There is a theoretical concept called the multiverse that some physicists have proposed to explain the properties of dark energy. The cosmological constant, which describes the energy density of dark energy, has a value that appears to be extraordinarily fine-tuned. If it were slightly larger, the universe would have expanded so rapidly that no galaxies, stars, or planets could have formed. If it were slightly smaller or negative, the universe might have collapsed back on itself. The observed value sits in a narrow range that permits the existence of complex structures and ultimately observers like us. Some physicists, including Steven Weinberg, proposed before dark energy was even discovered that the cosmological constant might take different values in different regions of a vast multiverse, and that we necessarily find ourselves in a region where the value permits our existence. This is called the anthropic principle, and it remains one of the most controversial ideas in modern physics. If the multiverse exists, then the darkness of our universe, shaped by the specific value of dark energy, is just one possibility among an unimaginably vast ensemble of different universes with different properties. There is something called vacuum decay that represents perhaps the most dramatic possible future for the darkness of the universe. The vacuum of space, the empty void that fills the gaps between particles and atoms, may not be in its lowest possible energy state. It may be in a metastable state, a local minimum that is not the true minimum. If this is the case, then somewhere, at some point, a quantum fluctuation could cause the vacuum to tunnel to its true lowest energy state, releasing an enormous amount of energy and creating a bubble of true vacuum that would expand at the speed of light, destroying everything it touches. Inside the bubble, the laws of physics would be different. Particles, atoms, and all familiar structures would cease to exist. The bubble would be undetectable until it arrived, because it travels at the speed of light, and no warning signal can outrun it. This is the most extreme form of cosmic darkness, a darkness that erases not just light, but the very possibility of light. Current evidence suggests that vacuum decay, if possible at all, is extraordinarily unlikely on any timescale that matters for human civilization. The Higgs field measurements from the Large Hadron Collider suggest that the vacuum may be metastable, but the expected lifetime before decay is many, many orders of magnitude longer than the current age of the universe. It is a theoretical possibility, not an imminent threat, but it is a reminder that the darkness of the universe may have depths that we have not yet fathomed. Light takes time to travel, and this simple fact creates a phenomenon called the look-back time. When astronomers say that a galaxy is 10 billion light-years away, they mean that the light we are seeing from that galaxy has been traveling for 10 billion years. We are seeing the galaxy as it was 10 billion years ago, not as it is today. This means that the observable universe is not a snapshot of the cosmos as it exists at this moment. It is a composite of light from different epochs, layered together by the finite speed of light. The nearby universe appears as it is now. The distant universe appears as it was in the past. The most distant things we can see appear as they were in the infancy of the cosmos. The night sky is not a window into space alone. It is a window into time. There is a paradox at the heart of modern cosmology. We live in the most luminous era the universe has ever known. More stars are burning right now than at any time in the past, and yet the sky is dark. It is dark because the universe is vast beyond comprehension, because light has a finite speed, because space is expanding and stretching light into invisibility, and because 95% of the universe's content is made of invisible substances we have never directly detected. The darkness is not a failure of light. It is a statement about the nature of reality itself. It tells us that the universe is bigger than light can fill, older than light can reach, and stranger than light alone can reveal. Every photon of starlight that reaches your eyes has completed an almost miraculous journey. It was born in the nuclear furnace of a star, where hydrogen atoms are fused into helium at temperatures of millions of degrees. It then spent thousands or even hundreds of thousands of years bouncing randomly through the dense interior of the star, absorbed and re-emitted billions of times before finally reaching the surface. From there, it launched into the void at 186,000 miles per second, crossing light years of empty space, passing through clouds of interstellar dust, perhaps being bent by the gravity of a galaxy along the way, until it finally entered the atmosphere of Earth, passed through layers of nitrogen and oxygen, and landed on the retina of your eye. There it triggered a chemical reaction in a single rod or cone cell, sending an electrical signal to your brain that you interpreted as a point of light in the night sky. Every star you see is the end of a journey that began in nuclear fire and ended in the quiet chemistry of your own biology. The sun produces about 3.8 times 10 to the power of 26 watts of energy every second. That is 380 trillion watts. Most of that energy radiates outward into space in every direction, and only a tiny fraction, about 1/2 billionths, is intercepted by the Earth. The rest continues outward, spreading thinner and fainter with every passing light year, until it is just another faint contribution to the extragalactic background light. From a distance of just 4 light years, our sun would appear as an ordinary, unremarkable star. From across the galaxy, it would be invisible to the naked eye. From another galaxy, it would be utterly undetectable as an individual object. The light of even the most powerful star is humbled by the vastness of the space it must fill. There are stars that are intrinsically far more luminous than the sun. The star Rigel in the constellation Orion is a blue supergiant, roughly 120,000 times more luminous than the sun. It is one of the brightest stars in the sky despite being about 860 light-years away. The star Deneb in the constellation Cygnus is even more extreme, approximately 200,000 times more luminous than the sun, and about 2,600 light-years away. These stars are so luminous that they are visible across enormous distances. And yet, even Deneb, one of the most luminous stars in our region of the galaxy, would be invisible from the Andromeda Galaxy. The distance swallows everything. There is a type of event called a gamma-ray burst that produces more energy in a few seconds than the sun will emit in its entire 10 billion year lifetime. Gamma ray bursts are the most energetic events in the universe since the Big Bang. They are produced by the collapse of massive stars into black holes, or by the merger of neutron stars. For a few seconds, a gamma ray burst can outshine the entire observable universe in gamma rays. And yet, because they are so brief and so distant, they are invisible to the naked eye. They occur in the darkness of the sky, flash for a moment in wavelengths our eyes cannot detect, and are gone. Only space-based gamma-ray telescopes, like NASA's Fermi Gamma Ray Space Telescope and the Neil Gehrels Swift Observatory, can catch them. The most violent events in the cosmos are hidden in the darkness. The cosmic web, the large-scale structure of the universe, has been mapped in increasing detail by surveys like the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey. These surveys have measured the positions and distances of millions of galaxies, revealing a structure that looks remarkably like a three-dimensional web. Galaxies are concentrated along filaments and walls that surround vast empty voids. The largest known structure is the Hercules Corona Borealis Great Wall, a colossal filament of galaxies approximately 10 billion light-years across. It is so large that light takes 10 billion years to cross from one side to the other. And between these filaments, the voids yawn dark and nearly empty, bubbles of nothing in a web of everything. There are galaxies that are almost entirely dark. These are called ultra-diffuse galaxies, and they are roughly the same size as the Milky Way, but contain only a tiny fraction of the stars. The galaxy Dragonfly 44, discovered in 2016, is about the same size as the Milky Way, but has only 1% of the stars. Its mass, however, is comparable. The difference is made up almost entirely of dark matter. Dragonfly 44 is a galaxy made of darkness, a vast dark matter halo with a faint dusting of stars, like a few candles in a cathedral. It raises profound questions about galaxy formation. How can a galaxy acquire so much dark matter and so few stars? What determines whether the raw materials of a galaxy ignite into starlight or remain forever dark? There is another class of objects called dark galaxies, which are hypothesized to contain no stars at all. These would be dark matter halos that never accumulated enough ordinary matter or never reached the right conditions for star formation to begin. They would be entirely invisible in optical light. Astronomers have searched for them using radio telescopes, looking for the 21-centimeter emission of neutral hydrogen, and through gravitational lensing, looking for the telltale distortion caused by their invisible mass. A few candidates have been identified, but the existence of truly starless dark galaxies remains an open question. If they exist, the universe may contain vast numbers of invisible structures, galaxies in every sense except for the one that makes them visible. Light. Rogue planets are another form of cosmic darkness. These are planets that have been ejected from their parent solar systems through gravitational interactions and now drift through interstellar space, unbound to any star. They receive no starlight. Their surfaces are frozen and dark. In 2011, a study based on gravitational microlensing observations estimated that there may be billions of rogue planets in the Milky Way alone, possibly outnumbering the stars. If this estimate is correct, the galaxy is filled with dark, cold worlds, wandering the void in permanent night. Some may be gas giants, others rocky worlds, drifting in temperatures just a few degrees above absolute zero. They are invisible except when they happen to pass in front of a more distant star and briefly magnify its light through gravitational lensing. The darkness between the stars is not just empty space, it is populated by worlds without suns. Brown dwarfs are objects that fall between the largest planets and the smallest stars. They form like stars by the gravitational collapse of gas clouds, but they lack enough mass to sustain the hydrogen fusion that powers true stars. A brown dwarf typically has between 13 and 80 times the mass of Jupiter. They glow faintly in infrared when young, heated by their formation and by the slow fusion of deuterium, but they cool over time and gradually fade. The oldest brown dwarfs are nearly invisible, emitting only the faintest traces of infrared radiation. They drift through the galaxy in vast numbers, dimmer than the dimmest stars, warmer than the coldest planets, occupying a twilight category between the lit and the unlit. There may be tens of billions of brown dwarfs in the Milky Way. They are the dim embers of a process that almost, but not quite, produced a star. There is a concept called the Olbers's paradox resolution summary, and it can be stated simply. The night sky is dark for three main reasons. First, the universe has a finite age, so light from the most distant objects has not yet had time to reach us. Second, the universe is expanding, which redshifts distant starlight into invisible wavelengths. And third, stars have finite lifetimes, so not every direction in the sky is occupied by a currently shining star. These three factors, time, expansion, and stellar mortality, conspire to give us the dark sky we see. But as we have explored tonight, the darkness is not simple. It is layered. It is complex. It hides dark matter, dark energy, ancient radiation, cosmic voids, rogue planets, and mysteries that the greatest minds in physics have not yet solved. The darkness is not empty. It is full. It is full of everything we have yet to understand. The night sky has been a source of wonder for every human culture that has ever existed. The ancient Egyptians saw the Milky Way as a celestial river. The Aboriginal Australians saw dark patches in the Milky Way as shapes, including the famous Emu in the sky, a dark nebula that stretches across the galactic plane. The ancient Greeks named the constellations after heroes and monsters. The Polynesians navigated thousands of miles of open ocean by the positions of the stars. For most of human history, the night sky was not just a curiosity. It was a map, a calendar, a source of myth, and a connection to something vast and incomprehensible. The darkness was the canvas. The stars were the story. In Aboriginal Australian astronomy, the dark spaces in the Milky Way are not absences but presences. The Emu in the sky is formed by dark nebulae, the same interstellar dust clouds that astronomers study with infrared telescopes. The head of the Emu is the dark Coal-Sack Nebula near the Southern Cross. Its body and legs are traced by dark lanes that wind through the Milky Way toward the galactic center. For the Kamilaroi people, the emu in the sky is connected to the emus on the ground. When the celestial emu is in a certain position, it signals the season when real emus are laying their eggs. The darkness of the sky was not just beautiful, it was practical. It carried information encoded in shadow. The cosmic dark ages, which we explored earlier, have a parallel in human history. Before the invention of the telescope in the early 17th century, humanity's understanding of the cosmos was limited to what could be seen with the naked eye. The universe appeared to be a relatively small sphere of stars surrounding the Earth. The idea that the darkness between stars might contain anything at all, let alone galaxies, dark matter, and the remnants of the Big Bang, would have been unimaginable. Every major advance in astronomy has been, in some sense, a revelation about the darkness. Each new instrument, from Galileo's telescope to the Hubble Space Telescope to LIGO, has peeled back another layer of the dark and revealed something astonishing hiding within it. There is a form of electromagnetic radiation that fills the universe and was produced not by the Big Bang itself, but by the processes that followed. The cosmic X-ray background is a diffuse glow of X-ray radiation that pervades the sky. first detected in 1962 by Riccardo Giacconi and his colleagues. It was initially mysterious, but astronomers have since determined that most of it comes from active galactic nuclei, supermassive black holes at the centers of distant galaxies that are actively accreting matter and producing X-rays. The cosmic X-ray background is another invisible glow filling the darkness, this one produced not by the primordial universe but by the ongoing activity of black holes across cosmic time. Even in X-ray light, the universe is not dark. It glows. The cosmic radio background is yet another pervasive glow, this one at radio wavelengths. It was first detected in the 1950s and includes contributions from many sources. Synchrotron radiation from electrons spiraling in galactic magnetic fields, radio emission from distant galaxies, and the cosmic microwave background itself at its longest wavelengths. In radio light, the sky is a tapestry of emission, with the Milky Way blazing across the center and distant radio galaxies scattered like sparks. The darkness we perceive is specific to the narrow range of wavelengths our eyes can detect. Step outside that range into radio, infrared, ultraviolet, X-ray, or gamma-ray wavelengths, and the sky lights up in different ways. Each wavelength reveals a different universe hiding in the same darkness. The total energy output of the universe has been measured. A project called the Galaxy and Mass Assembly Survey, or GAMMA, calculated in 2015 that the universe is producing about half as much energy as it was 2 billion years ago. Star formation across the universe peaked roughly 10 billion years ago and has been declining ever since. The universe is slowly fading. It is producing less light with each passing eon. The stars that are dying are not being fully replaced by new ones. The raw materials for star formation, primarily hydrogen gas, are being consumed and not replenished. The universe is, in a very real sense, running out of fuel. The lights are going out, slowly, but going out nonetheless. This decline in star formation has been measured by multiple surveys and space telescopes. The Hubble Space Telescope, the Herschel Space Observatory, and the James Webb Space Telescope have all contributed to our understanding of how the cosmic star formation rate has changed over time. At its peak, roughly 10 billion years ago, the universe was forming stars at roughly 10 times the current rate. Galaxies were smaller, more chaotic, richer in gas, and more actively merging with each other. The universe was a younger, more violent, and more luminous place. Today, the great era of star formation is winding down. Most of the large galaxies in the local universe are dominated by older, redder stars, and their rates of new star production are modest compared to their youth. The universe has entered its middle age, and the sky is dimming accordingly. There is a poetic notion sometimes called the end of greatness. In cosmology, it refers to the scale above which the universe appears smooth and uniform, with no structures larger than about 1 billion light-years. Below this scale, the universe has a rich and complex structure: galaxies, clusters, filaments, and voids. Above it, everything averages out. The universe looks the same in every direction. This large-scale uniformity is one of the foundational observations of modern cosmology and is encoded in the cosmic microwave background. On the grandest scales, the universe is featureless. There are no superstructures, no privileged directions, no cosmic landmarks. There is only the smooth, expanding fabric of space-time, the same in every direction, stretching into a darkness that is uniform, isotropic, and without end. There are stars that are invisible not because they are faint, but because they are dead. White dwarfs, the remnants of stars like our Sun, are the most common stellar endpoint. A white dwarf is roughly the size of the Earth, but has a mass comparable to the Sun. When first formed, it is extremely hot, with surface temperatures around 100,000 degrees Celsius, and it glows brightly in ultraviolet and visible light. But over billions of years it cools. There is no energy source to sustain it. It simply radiates away its stored heat, growing cooler and dimmer with each passing epoch. Eventually, after a timescale longer than the current age of the universe, a white dwarf would cool to the point where it emits no detectable radiation. It would become a black dwarf, a cold, dark, Earth-sized crystal of carbon and oxygen, invisible against the blackness of space. No black dwarfs are thought to exist yet, because the universe is not old enough for any white dwarf to have fully cooled. But in the far future, they will be among the most common objects in the cosmos. Dark, cold remnants of stars that once shone. There are places in the universe where light is being destroyed. When a photon falls into a black hole, it crosses the event horizon and is lost from the observable universe. The information it carried, the record of the star that produced it, the wavelength that encoded its history, is swallowed by the black hole and, according to classical general relativity, destroyed. Stephen Hawking argued that black holes do eventually return energy to the universe in the form of Hawking radiation, a faint thermal glow produced by quantum effects near the event horizon. But Hawking radiation is extraordinarily faint. For a stellar mass black hole, the temperature of Hawking radiation is far below the temperature of the cosmic microwave background, making it completely undetectable against the ambient glow of the universe. Black holes are currently net consumers of light. They take in more than they give back. They are the universe's ultimate shadows. Yet even shadows carry information. The shadow of a black hole, as imaged by the Event Horizon Telescope, is not just an absence. It is a precisely shaped region whose size and geometry are determined by the black hole's mass and spin. By studying the shadow, astronomers can measure properties of the black hole that would otherwise be invisible. The darkness of the shadow is, paradoxically, one of the most information-rich features in the image. The absence of light tells us about the presence of extreme gravity. In the universe, even darkness speaks. There is a form of matter called antimatter that, when it meets ordinary matter, annihilates in a burst of pure energy, converting both particles entirely into photons. In the early universe, matter and antimatter were produced in nearly equal amounts. When they met, they annihilated, producing the sea of photons that would eventually become the cosmic microwave background. But for reasons that are not fully understood, there was a tiny imbalance, roughly one extra particle of matter for every billion matter-antimatter pairs. When the annihilation was complete, that tiny surplus of matter was left behind, and it is from that remnant that every star, planet, and living thing in the universe is made. The visible universe is the leftovers of a vast cosmic annihilation. The light of the cosmic microwave background is the memorial of the matter and antimatter that were destroyed. The darkness between the stars is possible only because of this ancient, unexplained asymmetry. The origin of this matter, antimatter asymmetry, is one of the great unsolved problems in physics. It is called baryogenesis, and despite decades of theoretical and experimental work, no satisfactory explanation has been found. The standard model of particle physics predicts a slight asymmetry, but not nearly enough to account for the observed excess of matter. Something beyond our current understanding of physics must have tipped the balance. If the asymmetry had not occurred, the universe would contain nothing but radiation. No matter, no atoms, no stars, no darkness, because there would be no structures to cast shadows or to separate the light. The darkness of the night sky, the existence of a material universe at all, depends on a mystery we have not yet solved. There is a concept in physics called the arrow of time. The laws of physics, at the most fundamental level, do not distinguish between the past and the future. A video of two particles colliding looks the same whether played forward or backward, and yet the universe clearly has a direction. Time moves forward. Eggs break, but do not unbreak. Stars burn, but do not unburn. This directionality is linked to the second law of thermodynamics, which states that the entropy of a closed system always increases. Entropy is a measure of disorder, and the universe began in a state of extraordinarily low entropy, a hot, dense, uniform state from which all structure has since evolved. The arrow of time points from low entropy to high entropy, from order to disorder, from structure to heat death. The darkness of the future, the slow fading of stars, and the expansion into emptiness is a consequence of this arrow. The universe is not becoming dark by accident. It is becoming dark because the laws of physics demand it. The Hubble constant is a number that describes the current rate of expansion of the universe. It is named after Edwin Hubble and is measured in kilometers per second per megaparsec, which means that for every megaparsec, about 3.26 million light-years of distance, galaxies are receding at a certain additional velocity. The currently accepted value is approximately 67 to 74 kilometers per second per megaparsec, depending on the method of measurement. There is a well-known tension between different measurements. The value derived from the cosmic microwave background by Esai's Planck satellite is about 67.4, while the value derived from observations of nearby supernovae and Cepheid variable stars by teams using the Hubble Space Telescope is about 73. This discrepancy, known as the Hubble tension, has persisted despite extensive efforts to resolve it, and may indicate new physics beyond the current standard model of cosmology. The rate at which the universe is darkening depends on this number, and we are not yet certain what it is. There is beauty in the fact that the darkness of the sky is not one thing but many. It is the finite age of the universe, the expansion of space, the redshift of light, the absorption of dust, the overwhelming dominance of dark matter and dark energy, the faintness of distant galaxies, the limits of human vision, the interference of light pollution, and the slow winding down of star formation. Each layer of darkness tells a different story. Each is a window into a different aspect of physics. The night sky is not a blank canvas. It is a document written in shadow, encoding the history and future of the cosmos. When you look up at the sky on a clear, dark night, and you see the stars scattered across the blackness, you are looking at roughly 0.00000000001% of the stars in the observable universe. The rest are too faint, too far, or too redshifted to see. The darkness between the visible stars is not empty. It is filled with the invisible light of the cosmic microwave background, the gravitational pull of dark matter, the pressure of dark energy, the faint glow of interstellar dust, the passage of neutrinos and gravitational waves, and the ghosts of galaxies too distant to detect. The darkness is the universe's way of keeping most of its secrets, and the light you do see, those few thousand points scattered across the dome of the sky, is the universe's gift. A tiny, precious, breathtaking fraction of everything that exists, offered freely to anyone who takes a moment to look up. There are sounds in the darkness if you know how to listen. The cosmic microwave background, when converted into sound waves, produces a deep, low hum, a tone that corresponds to the acoustic oscillations of the early universe. Before atoms formed, the universe was filled with a plasma that supported sound waves, density fluctuations that propagated through the medium like pressure waves through air. These oscillations left their imprint on the cosmic microwave background as patterns of slightly hotter and cooler spots. When scientists analyze these patterns, they find a fundamental frequency and its harmonics, the cosmic equivalent of a musical chord. The universe, in its first 380,000 years, was ringing like a bell. The note has long since faded, but its echo is preserved in the microwave glow that fills the sky. There is a phenomenon called baryon acoustic oscillations that represents the frozen remnants of those ancient sound waves. As the universe expanded and cooled, the sound waves that had been propagating through the plasma were locked in place when atoms formed and the plasma became neutral gas. The density variations caused by these waves were preserved in the distribution of matter, and they can be detected today as a slight preference for galaxies to be separated by a characteristic distance of about 490 million light-years. This preferred separation shows up as a bump in the galaxy correlation function, a statistical measure of how galaxies are distributed in space. It is the largest known pattern in the universe, a fossil sound wave from the first moments of cosmic history, imprinted on the arrangement of galaxies across billions of light-years. The night sky is not the same in every direction, even apart from the stars. The cosmic microwave background has a very slight asymmetry called the dipole anisotropy, caused by the motion of the Earth through the sea of microwave photons. Because the Earth, the Sun, and the Milky Way are all moving through space, the microwave background appears slightly hotter in the direction we are moving toward and slightly cooler in the direction we are moving away from. This dipole has been measured precisely and indicates that the solar system is moving at about 370 kilometers per second relative to the rest frame of the cosmic microwave background. This motion has a direction, roughly toward the constellation Leo. Every moment, we are hurtling through the ancient light of the Big Bang at hundreds of kilometers per second, and the asymmetry of the darkness around us records our velocity. There are galaxies that are almost completely dark in visible light, but blaze in other wavelengths. Sub-millimeter galaxies, detected primarily at wavelengths between infrared and radio, are among the most luminous galaxies in the universe, but their light is almost entirely absorbed by thick clouds of dust and re-emitted at longer wavelengths. They are invisible to optical telescopes. Only instruments like the James Clerk Maxwell Telescope, the Atacama Large Millimeter Array, and the Herschel Space Observatory can see them. These galaxies are often undergoing intense bursts of star formation, producing hundreds or even thousands of solar masses worth of new stars per year. Yet they are shrouded in so much dust that virtually no visible light escapes. They are among the most active places in the universe, and they are hidden in the darkness. There is a faint glow in the darkness between galaxies that has puzzled astronomers. Observations from the New Horizons spacecraft, now far beyond Pluto in the outer solar system, have measured the brightness of the cosmic optical background, the total amount of visible light in the universe from all sources. Surprisingly, the measurements suggest that there is more light than can be accounted for by known galaxies. The excess is small but persistent. Its origin is debated. Some scientists suggest it may come from faint, unresolved dwarf galaxies too small to be detected individually. Others suggest it may be light from stars stripped from galaxies during mergers, now wandering freely through intergalactic space. Still others have proposed more exotic explanations, including the decay of unknown particles. The darkness between galaxies may be slightly less dark than we thought, and the reason is a mystery. The human experience of darkness is not purely visual. In darkness, other senses sharpen. Hearing becomes more acute. The sense of touch becomes more sensitive. The brain, deprived of visual input, reallocates its processing resources to other modalities. This is not imagination. Studies have shown measurable changes in auditory sensitivity in dark environments. Darkness, for a living creature, is not simply the absence of light. It is a different mode of being, one in which the brain reconfigures itself to extract maximum information from the remaining senses. We are built for darkness. We have spent half of our evolutionary history in it, and our brains carry the imprint of those millions of years of nighttime adaptation. Sleep itself is tied to darkness in fundamental ways. The hormone melatonin, which regulates the sleep-wake cycle, is produced by the pineal gland in response to darkness. When light levels drop, melatonin production increases, signaling to the body that it is time to rest. This process is ancient, shared by virtually all vertebrates and many invertebrates. It ties the biology of sleep to the rotation of the earth and ultimately to the darkness of the night sky. When you feel drowsy as the evening deepens, you are responding to the same darkness that puzzled Olbers and inspired Hubble. Your body is synchronized to the spinning of a planet, which is synchronized to the light of a star, which is one of hundreds of billions in a galaxy that floats in the dark. There is a region of intergalactic space called the Lyman Alpha Forest. It is not a physical place, but a pattern in the light from distant quasars. When the light from a quasar passes through intergalactic space on its way to Earth, it encounters thin clouds of neutral hydrogen. Each cloud absorbs light at a specific wavelength determined by its distance and velocity, creating a dark absorption line in the quasar spectrum. Because there are many such clouds along the line of sight, the spectrum is filled with dozens or hundreds of absorption lines, creating a dense, forest-like pattern. This Lyman Alpha Forest is a map of the intergalactic medium, the thin, faint gas that fills the spaces between galaxies. It shows that even the emptiest regions of the universe are not truly empty. They are threaded with gossamer filaments of gas, remnants of the cosmic web, too thin to form stars, but dense enough to leave their mark on passing light. There is a limit to how dark the universe can be, even in principle. Quantum mechanics tells us that the vacuum of space is never truly empty. It is filled with quantum fluctuations, brief, random variations in the energy of the vacuum that produce virtual particles. These fluctuations are real and have measurable effects. The Casimir effect, first predicted in 1948 and experimentally confirmed in 1997, shows that two parallel metal plates placed very close together in a vacuum experience a small attractive force caused by the difference in vacuum energy between the plates and outside them. The vacuum has energy, and that energy is everywhere. Even if you could remove every particle, every photon, every neutrino, and every gravitational wave from a region of space, the quantum vacuum would remain, buzzing faintly with the energy of virtual fluctuations. Perfect darkness, in the quantum sense, is impossible. The universe always has a floor, a minimum level of activity that can never be reduced to zero. There is something called the Unruh effect that connects darkness to acceleration in a surprising way. According to theoretical physicist William Unruh, an observer accelerating through the vacuum of space would perceive a warm bath of particles, where a stationary observer would perceive nothing. The faster the acceleration, the higher the temperature of the perceived radiation. This means that what counts as darkness, as emptiness, depends on the observer's motion. For an astronaut in freefall, the vacuum is cold and empty. For an astronaut accelerating at enormous rates, the same vacuum would glow with detectable radiation. Darkness is not absolute. It is relative. It depends on who is asking and how they are moving through space. There is a deep connection between darkness and information. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, and that entropy is proportional to the area of the event horizon, not the volume. This was a profound and surprising result. It suggested that the maximum amount of information that can be contained in a region of space is determined by the area of the boundary, not the volume of the interior. This idea led to the holographic principle, which proposes that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary. If the holographic principle is correct, then the three-dimensional darkness of space may be, in some deep sense, a projection. The volume of the void may be described entirely by information written on its edges. Darkness, emptiness, and space itself may be emergent properties of a more fundamental, two-dimensional reality. There is a phenomenon called gravitational time dilation that connects darkness to the flow of time. Near a massive object, time runs more slowly than it does far away. This has been measured with extraordinary precision using atomic clocks. A clock on the surface of the Earth runs slightly slower than a clock on a satellite in orbit. A clock near a neutron star would run much slower, and at the event horizon of a black hole, time, from the perspective of a distant observer, stops entirely. An object falling into a black hole would appear, to an outside observer, to slow down and freeze at the event horizon, its light stretching to infinitely long wavelengths and fading to nothing. The object would appear to hover at the boundary forever, growing dimmer and redder, but never quite disappearing. The darkness of a black hole is also a place where time itself is distorted beyond recognition. The night sky contains ancient light from the very first generation of stars, though we have not yet seen it directly. Population 3 stars, the first stars to form after the Dark Ages, are believed to have been massive, luminous, and short-lived. They burn through their hydrogen fuel in just a few million years before exploding as supernovae or collapsing into black holes. Their light has been redshifted by the expansion of the universe into the infrared, and it is mixed with the light from billions of subsequent generations of stars. Distinguishing the light of the very first stars from the background glow of everything that came after is one of the great challenges of observational cosmology. The James Webb Space Telescope is searching for these primordial signatures, looking for the faint, red-shifted echoes of the first fires that broke the cosmic darkness. There is a profound asymmetry in the night sky that most people never notice. The Milky Way divides the sky roughly in half. On one side of the galactic plane, you can see deep into the universe. On the other, the view is the same. But along the plane itself, the dust and gas of the galaxy block our view almost completely. The zone of avoidance, as mentioned earlier, hides perhaps 20% of the extragalactic universe from optical telescopes. Behind the Milky Way's dusty veil, there are galaxy clusters, cosmic voids, and large-scale structures that we can only glimpse in infrared and radio wavelengths. One of the largest nearby structures hidden in the zone of avoidance is the Great Attractor, a gravitational anomaly in the direction of the Centaurus and Norma constellations that appears to be pulling the Milky Way and thousands of nearby galaxies toward it at about 600 kilometers per second. For decades, the Great Attractor was a mystery, hidden behind the dust of our own galaxy. It turns out to be part of a much larger structure called the Laniakea supercluster, a vast basin of gravitational attraction containing about 100,000 galaxies. Our Milky Way sits on the outskirts of this structure, falling slowly inward. The darkness of the zone of avoidance was hiding our own cosmic neighborhood from us. There is an instrument called DESI, the Dark Energy Spectroscopic Instrument, which began operations in 2021. DESI is a ground-based instrument mounted on a telescope in Arizona, and it is one of the most ambitious surveys ever undertaken. It is designed to measure the spectra of over 30 million galaxies and quasars over a 5-year period, mapping the three-dimensional structure of the universe across an enormous volume. By measuring how the distribution of galaxies has changed over time, DESI will constrain the properties of dark energy with unprecedented precision. Early results from DESI, released in 2024, provided intriguing hints that dark energy may not be perfectly constant, but may vary slightly over time. If confirmed, this would be one of the most significant discoveries in cosmology since the original detection of dark energy in 1998. The darkness of the universe may not be static. It may be evolving. There is a phenomenon that occurs in the upper atmosphere of the Earth called airglow. Even on the darkest nights, far from any artificial light, the sky is not perfectly black. The atmosphere itself emits a faint light, produced by chemical reactions in the upper atmosphere, primarily the recombination of atoms and molecules that were split apart by ultraviolet radiation from the sun during the day. Airglow is visible from space as a thin, luminous shell surrounding the Earth, typically greenish in color. From the ground, it contributes a subtle diffuse brightness to the night sky that limits the faintest objects visible to even the most powerful ground-based telescopes. Space telescopes orbiting above the atmosphere are free from this contamination. The atmosphere is not merely a window to the cosmos. It is a faintly glowing curtain, and the stars we see are viewed through its soft radiance. The darkness of the universe has inspired some of the most beautiful writing in the history of science. Carl Sagan, in his book, Pale Blue Dot, described the Earth as seen from the Voyager 1 spacecraft at a distance of 6 billion kilometers. A tiny, faint dot suspended in a sunbeam against the vast darkness of space. That is here, he wrote. That is home. That is us. The darkness in that image is not threatening. It is the context that gives the pale blue dot its meaning. Without the darkness, the smallness and preciousness of our world would not be apparent. The darkness is what makes the light meaningful. There's a measurement called the surface brightness of the night sky, and it is expressed in magnitudes per square arc second. A truly dark sky, far from light pollution, has a surface brightness of about 21.5 to 22.0 magnitudes per square arc second in the visual band. This means that each tiny patch of sky, 1 arc second on a side, has a brightness equivalent to a star of that magnitude. The faintest stars visible to the naked eye are about magnitude 6. The sky itself is much fainter, but it is not zero. Even the darkest sky has a measurable brightness, contributed by airglow, scattered starlight, zodiacal light, and the faint, unresolved glow of distant galaxies. Perfect darkness, even on the darkest night, in the most remote location on Earth, is never quite achieved. There is a concept in cosmology called the end of the stelliferous era. The stelliferous era is the current epoch of the universe, the period during which stars shine. It began with the first stars, roughly 200 million years after the Big Bang, and it will end when the last star burns out. The last stars to die will be the smallest red dwarfs, which burn their hydrogen fuel so slowly that they can shine for trillions of years. The smallest known red dwarfs have masses about 8% that of the Sun and surface temperatures of only about 2,000 degrees Celsius. They are dim, cool, and extraordinarily long-lived. A red dwarf with a mass of about 0.08 solar masses could, in theory, continue burning for roughly 10 trillion years, nearly 1,000 times the current age of the universe. When the last of these tiny stars finally exhausts its fuel and fades, the stelliferous era will end. The universe will enter an era of darkness that will last far, far longer than the age of light. After the stelliferous era comes the degenerate era, dominated by white dwarfs, neutron stars, and brown dwarfs. These objects do not produce energy through fusion. They simply cool. The universe during this era will be profoundly dark, lit only by the faint thermal glow of cooling remnants and the occasional flash of energy from rare events, such as the collision of brown dwarfs or the accretion of interstellar gas by a white dwarf. These flashes will become rarer and rarer as the remaining matter is consumed or dispersed. The degenerate era is expected to last from roughly 10 to the power of 14 years to perhaps 10 to the power of 40 years, depending on the rate of proton decay, if protons decay at all. If protons are stable, the degenerate era could last much longer. But many theories of particle physics predict that protons are not stable, that they decay with a half-life of roughly 10 to the power of 36 to 10 to the power of 41 years. If this is the case, then over unimaginably long timescales, all the matter in white dwarfs, neutron stars, and every other structure made of ordinary matter will slowly dissolve into lighter particles and radiation. The solid remnants of the stellar era will evaporate, atom by atom, into a thin haze of photons, electrons, positrons, and neutrinos. The universe will lose its material substance, not through explosion or catastrophe, but through the slow, patient, inevitable ticking of quantum probability. After the era of proton decay comes the black hole era. By this point, the only remaining organized structures will be black holes. Everything else will have decayed or dispersed. The black holes will slowly evaporate through Hawking radiation, converting their mass into a faint trickle of photons and particles. The largest black holes, the supermassive ones at the centers of former galaxies, will be the last to go, persisting for roughly 10 to the power of 100 years. When the last black hole evaporates, there will be nothing left. No matter, no structure, no energy gradients, only a vast, cooling, ever-expanding void filled with photons so long in wavelength that they carry essentially no energy. This is the dark era. It will last forever. There is an open question about whether anything interesting can happen in the dark era. Some physicists have speculated about the possibility of Boltzmann brains, random configurations of particles that, through pure quantum fluctuation, happen to form a conscious entity for a brief instant before dissipating. Over truly infinite timescales, even the most improbable events must eventually occur, and a Boltzmann brain, while extraordinarily unlikely at any given moment, would become inevitable given enough time. This idea is more a philosophical curiosity than a scientific prediction, but it highlights the strange nature of eternity. In the dark era, with infinite time and no competing processes, the universe's only events might be the rarest fluctuations imaginable. Brief sparks of improbable order in an ocean of endless night. There is a theory called conformal cyclic cosmology, proposed by the mathematician and physicist Roger Penrose. In this theory, the heat death of the universe is not the end, but a transition. As the universe empties out and all massive particles decay, the remaining radiation becomes the only content of the cosmos. In a universe containing only radiation, the distinction between large and small scales loses meaning, and the geometry of space-time becomes conformally equivalent to the hot, dense state at the beginning of a new Big Bang. Penrose proposes that the end of one cosmic era seamlessly becomes the beginning of another, with the death of one universe giving birth to the next. If this theory is correct, the ultimate darkness is not an ending. It is a threshold. The universe may be cyclic, endlessly dying and being reborn, with each cycle separated by a passage through perfect darkness. The darkness of the universe is layered, and each layer has its own story. There is the darkness of the finite speed of light, which creates a horizon beyond which we cannot see. There is the darkness of cosmic expansion, which stretches light into invisibility. There is the darkness of interstellar dust, which absorbs and scatters starlight. There is the darkness of dark matter, which shapes the universe but never reveals itself in light. There is the darkness of dark energy, which accelerates the expansion and determines the fate of everything. There is the darkness of the cosmic dark ages, when no stars had yet formed. There is the darkness of black holes, where light itself is trapped. And there is the darkness of the far future, when the last stars will have burned out and the universe will enter an eternal night. Each of these layers is a chapter in the story of the cosmos, and together, they answer the question we began with tonight. Why is the universe dark? Not because there is no light, but because the light is finite and the darkness is vast. Because space is expanding faster than light can fill it. Because most of the universe is made of things that do not shine. Because even the brightest stars are tiny sparks in an ocean of void. And because the era of light, the era in which we live and breathe and wonder, is a brief and precious chapter in a story that is mostly written in shadow. There is a measurement called the optical depth of the universe. It describes how transparent the cosmos is to light at different wavelengths. In the present-day universe, the optical depth in visible light is very low, meaning that the universe is almost perfectly transparent. A photon emitted by a distant galaxy can travel billions of light years without being absorbed or scattered. The universe was not always this way. Before the formation of atoms 380,000 years after the Big Bang, the optical depth was enormous. The universe was opaque. Photons could not travel more than a short distance before being absorbed by free electrons. The transition from opaque to transparent, called recombination, was one of the most dramatic events in cosmic history. In a cosmically brief period, the universe went from being a thick, impenetrable fog to being almost perfectly clear. The darkness of the sky is a consequence of that clarity. If the universe had remained opaque, we would see not darkness but a uniform glow in every direction, the light of the primordial fog pressing in from all sides. There is a phenomenon in astronomy called extinction, and it has nothing to do with the disappearance of species. Astronomical extinction refers to the dimming and reddening of starlight as it passes through interstellar dust. Even a thin veil of dust particles, each one smaller than a grain of sand, can absorb and scatter enough light to significantly reduce the apparent brightness of a distant star. The effect is wavelength dependent. Shorter wavelengths, like blue light, are scattered more than longer wavelengths, like red light. This means that distant stars appear redder and fainter than they actually are, a phenomenon called interstellar reddening. The night sky would appear noticeably different without interstellar dust. More stars would be visible. The Milky Way would appear brighter and bluer, and the dark lanes that wind through the galactic plane would vanish, replaced by a continuous band of starlight. The darkness within our galaxy is partly artificial, created by the dust that floats between the stars. There is an extraordinary telescope called the Vera C. Rubin Observatory, currently under construction in Chile, that will begin its primary survey in the mid-2020s. Named after the astronomer who provided definitive evidence for dark matter, the Rubin Observatory will survey the entire visible sky every few nights using a 3.2 gigapixel camera, the largest digital camera ever built. Over its 10-year survey, it will catalog billions of galaxies, millions of supernovae, and countless other transient events. One of its primary goals is to study dark energy by measuring how the distribution and shapes of galaxies change over time. Another is to detect objects in our own solar system, including potentially hazardous asteroids and distant objects in the Kuiper Belt. The Rubin Observatory will transform our understanding of both the darkness between galaxies and the darkness within our own cosmic neighborhood. There's a property of the universe called isotropy, which means that, on the largest scales, the universe looks the same in every direction. This has been confirmed by observations of the cosmic microwave background, which is uniform to within 1 part in 100,000. It has also been confirmed by galaxy surveys, which show that the statistical properties of galaxy distributions are the same in every direction when averaged over sufficiently large volumes. Isotropy is one of the cornerstones of the standard model of cosmology. It means that the darkness of the sky is the same everywhere. There is no preferred direction in the universe. No matter where you stand, no matter which way you look, the cosmic view, on the largest scales, is statistically identical. The darkness is democratic. It belongs equally to every observer, in every galaxy, in every direction. There is a property related to isotropy called homogeneity, which means that the universe looks the same from every location, not just every direction. Combined, isotropy and homogeneity form the cosmological principle, the foundational assumption of modern cosmology. It states that, on sufficiently large scales, the universe has no special places and no special directions. This principle has been tested and confirmed by multiple observations, and it means that the darkness we observe from Earth is not unique to our location. An observer in the Andromeda Galaxy, or in a galaxy at the edge of the observable universe, would see a similar sky. A handful of nearby stars, the glow of their own galaxy, and beyond that, the same vast, dark expanse filled with the same faint backgrounds of microwave, infrared, and X-ray radiation. The darkness is universal. It is the shared experience of every possible observer in the cosmos. The interstellar medium, the gas and dust between the stars, has a temperature structure that reflects the energy sources around it. In regions near hot, luminous stars, the gas is heated to thousands or tens of thousands of degrees and glows in the ultraviolet and visible light. These regions are called emission nebulae and are some of the most beautiful objects in the sky. In regions far from any star, the gas cools to just a few degrees above absolute zero and emits only faint radio and infrared radiation. These cold regions are called molecular clouds, and they are the densest parts of the interstellar medium. Deep within molecular clouds, temperatures drop to as low as 10 degrees above absolute zero, and the gas condenses into clumps that will eventually collapse under their own gravity to form new stars. The darkest, coldest places in the galaxy are the birthplaces of stars. Darkness is not an endpoint. It is a beginning. There are particles called cosmic rays that travel through the darkness of space at nearly the speed of light. Cosmic rays are not rays at all, but high-energy subatomic particles, mostly protons and atomic nuclei, accelerated to extreme velocities by supernova explosions, black hole jets, and other violent cosmic events. The most energetic cosmic rays have energies exceeding 10 to the power of 20 electron volts, far greater than anything achievable by human-made particle accelerators. These particles travel across galaxies and even across intergalactic space, striking the Earth's atmosphere and producing cascades of secondary particles called air showers. Cosmic rays are invisible. They carry no light, but they are everywhere, filling the darkness of space with a constant rain of high-energy particles that have been traveling, in some cases, for millions of years. There are magnetic fields that thread through the darkness of intergalactic space. These fields are extraordinarily weak, roughly 1,000,000 times weaker than the Earth's magnetic field, but they extend across millions of light years and permeate the cosmic web. Their origin is not fully understood. They may have been generated by the motions of charged particles in the early universe amplified by the turbulent flows of gas in forming galaxies and spread throughout intergalactic space by galactic winds and the jets of active galactic nuclei. These fields are invisible in every sense. They produce no light, cast no shadow, and have almost no detectable effect on the matter around them. Yet they are real, measurable through their effect on the polarization of radio waves passing through them. The darkness of intergalactic space is threaded with invisible magnetism, a faint and ancient field whose origin and purpose remain unknown. There is a substance called intergalactic dust, distinct from the interstellar dust within galaxies. This dust exists in the vast spaces between galaxies, expelled from galaxies by supernova explosions, galactic winds, and the tidal forces of galaxy interactions. It is extraordinarily sparse, even more sparse than interstellar dust, but it is present. Observations using the absorption and reddening of light from distant quasars suggest that intergalactic dust may contribute a small but measurable dimming of distant objects. It adds another faint layer to the darkness of the sky, a thin veil of particles scattered across the voids between galaxies, contributing imperceptibly to the dimming of the cosmic light. There is a class of astronomical objects called blazars that represent some of the most extreme phenomena in the dark universe. A blazar is an active galactic nucleus powered by a supermassive black hole whose relativistic jet of plasma happens to be aimed almost directly at Earth. Because the jet is pointing toward us, its emission is enormously amplified by relativistic effects, making blazars among the brightest objects in the sky at certain wavelengths. They can vary in brightness by factors of 100 or more over timescales of hours to days. Despite their extreme luminosity, blazars are invisible to the naked eye because they are so distant, typically billions of light years away, and because much of their emission is in gamma rays and X-rays rather than visible light. The darkest regions of the sky may harbor blazars, objects whose concentrated beams of radiation would be blindingly bright if they were nearby, but which, from their actual distances, contribute only faintly to the cosmic background. There are satellite galaxies orbiting the Milky Way that are so faint they are almost invisible. These ultra-faint dwarf galaxies contain only a few thousand stars and are dominated by dark matter. The faintest known, such as Segway 1 and Willman 1, have luminosities less than 1,000th that of a typical globular cluster. They were only discovered in the early 2000s through careful analysis of survey data, and their existence has provided important constraints on the properties of dark matter. The number of ultra-faint dwarfs orbiting the Milky Way is still uncertain, and many more may await discovery, hidden in the darkness of the sky, too faint for current surveys to detect. The Milky Way may be surrounded by a swarm of invisible companions, each one a tiny galaxy held together by an invisible scaffolding of dark matter. There are neutrinos from the sun streaming through the darkness right now. Every second, about 65 billion solar neutrinos pass through every square centimeter of the Earth's surface. They are produced by the nuclear fusion reactions in the sun's core, and they travel at nearly the speed of light, passing through the Earth as if it were not there. Neutrino detectors, such as the Super Kamiokande detector in Japan and the Sudbury Neutrino Observatory in Canada, have confirmed the flux and properties of solar neutrinos, solving a decades-long mystery about why fewer neutrinos were detected than expected. The solution turned out to be that neutrinos oscillate between three types, or flavors, as they travel, and earlier detectors could only see one type. The darkness of space is filled with these ghostly particles, each one a messenger from the heart of a star, passing through matter almost without interaction. There are ancient photons from the cosmic microwave background that have been traveling for 13.8 billion years and are only now arriving at the Earth. Each one has been stretched by the expansion of the universe from a wavelength of about 1 micrometer in the infrared to about 1 millimeter in the microwave. Each one carries information about the state of the universe when it was only 380,000 years old. Each one has crossed the entire observable universe, traveling through voids and past galaxies and through the cosmic web without being absorbed or scattered, arriving as a faint pulse of energy that can only be detected by sensitive radio receivers cooled to near absolute zero. These photons are everywhere. They fill every cubic centimeter of space. There are about 411 cosmic microwave background photons in every cubic centimeter of the universe. You are immersed in them right now. They are the most numerous photons in existence, and they are completely invisible. The darkness around you is drenched in the oldest light in the universe. There is a concept called the last scattering surface, and it represents the most distant thing we can ever see with light. It is the surface from which the cosmic microwave background photons were released 380,000 years after the Big Bang. Today, due to the expansion of the universe, this surface is about 46 billion light years away. When we map the cosmic microwave background, we are essentially looking at the inside of a sphere centered on the Earth, a sphere whose radius is the distance to the last scattering surface. Everything beyond that sphere is hidden from electromagnetic observation. We can see back 13.8 billion years, but we cannot see back any further using light. The last scattering surface is the wall of our cosmic room. Beyond it, the universe continues, but it is dark to us. Not dark because it lacks light, but dark because its light has not yet reached us and perhaps never will. There is a thought experiment that beautifully illustrates the relationship between darkness and the structure of the universe. Imagine that you could see every photon at every wavelength that is passing through the space you currently occupy. You would see, in every direction, the faint glow of the cosmic microwave background. You would see infrared photons from distant, dust-shrouded galaxies. You would see X-ray photons from accretion disks around black holes. You would see gamma-ray photons from blazars and gamma-ray bursts. You would see radio photons from pulsars, synchrotron radiation, and the 21-centimeter glow of neutral hydrogen. You would feel the passage of neutrinos, ghostly and undetectable by your senses. You would detect the faint ripples of gravitational waves, distorting the fabric of space around you by amounts smaller than an atom. The space around you, which appears dark and empty to your eyes, is a roaring symphony of radiation, particles, and fields. The darkness is an illusion of limited perception. The universe is ablaze. And yet, here you are, a being made of atoms that were forged in the nuclear furnaces of stars that have long since died. A being whose eyes can detect photons that have traveled across light years of darkness to reach you. A being whose brain can contemplate the nature of dark matter, the expansion of space-time, and the ultimate fate of the cosmos. You are the universe looking back at itself, asking why it is dark, and beginning, slowly, beautifully to find the answer. The darkness is not your enemy. It is the canvas on which every point of light is painted. Without the darkness, there would be no stars. Without the vastness, there would be no wonder. Without the mystery, there would be no discovery. The universe is dark because it is vast, and it is beautiful because it is both. If sleep is close now, let it come. You have traveled far tonight, from the paradox of Olbers to the voids between galaxies, from the glow of the cosmic microwave background to the silent evaporation of black holes at the end of time. You have explored the hidden architecture of dark matter and the mysterious pressure of dark energy. You have looked into the deepest images ever taken of the cosmos and found thousands of galaxies hiding in what appeared to be empty darkness. You have listened to the echo of the Big Bang and felt the faint tug of gravity that connects you to everything that has ever existed. The darkness of the night sky is not empty. It is full of stories, and you have heard some of them tonight. Let them settle softly around you, like starlight arriving after a long journey. Let them remind you that you are part of something vast, ancient, and extraordinary. And let them carry you gently toward rest. Thank you for being here, for listening, for wondering. Your presence in this quiet corner of the universe means more than you know. If this journey brought you a moment of peace, a gentle tap on subscribe, or a quiet like, would help others find their way here too. And if you would like to continue exploring, another journey is waiting for you, right here, whenever you are ready. Until then, may the darkness around you feel not empty but full of ancient light, hidden galaxies, and the gentle hum of a universe that has been expanding, creating, and wondering for nearly 14 billion years. Good night, gentle soul. Rest well. The universe will be here when you wake, and remember, the darkness is not empty. It never was. It is the universe's way of holding its light gently, stretching it across time, spreading it across distances so vast that only wonder can follow. The darkness is patient. The darkness is full. And somewhere in it, right now, a photon that has been traveling for 13 billion years is arriving at a small blue planet where a quiet soul, resting in the dark, is just beginning to drift towards sleep. The universe is dark, and it is beautiful, and so are you.